The universe, for the most part, behaves itself. Stars burn through their fuel at predictable rates, planets trace ellipses around their suns with metronomic consistency, and galaxies spin like enormous patient pinwheels across billions of years. Tonight we're simply conducting a quiet audit of certain gravitational peculiarities, what you might call overachieving gravity wells, that have been accumulating entries in the cosmic ledger for quite some time. Nothing dramatic, nothing to worry about. Just a slow review of how an abstract mathematical curiosity became one of the central filing systems of modern astrophysics. In the 1700s, long before anyone had proper telescopes or any real sense of what stars actually were, two men independently stumbled onto an interesting calculation. John Migel, an English clergyman with a talent for natural philosophy, and Pierre-Simon Laplace, the French mathematician, both asked a simple question. What if an object was so massive and so compact that even light couldn't escape from it? At the time, light was thought to be made of tiny particles, little corpuscles zipping through space, and gravity was understood as a force that pulled on everything with mass. If light had mass, then gravity could slow it down, maybe even stop it entirely. They calculated something called escape velocity, the speed you'd need to break free from a gravitational pull, and realised that if you made an object massive enough or squeezed it down small enough, that escape velocity could exceed the speed of light. They called these hypothetical objects dark stars. The math was tidy, the logic sound, but without Einstein's relativity or any way to actually observe such things, the idea was filed away as a curious footnote. For more than a century it gathered dust in the margins of physics, an impractical thought experiment that led nowhere in particular. Then, in the early 20th century, Albert Einstein rewrote the rulebook. His general theory of relativity proposed something profoundly different. Gravity wasn't a force pulling objects together across empty space, but rather a consequence of mass telling space-time itself how to curve. Imagine the universe as a flexible grid, a vast sheet of graph paper that bends and warps wherever you place mass or energy on it. A planet rolls along the curves created by a star, not because the star is yanking on it with invisible strings, but because the planet is simply following the straightest possible path through curved geometry. Clocks tick at different rates depending on how deep you are in a gravitational well. Light, which always travels in straight lines locally, follows paths that appear bent when viewed from far away. Everything in the universe becomes a participant in this geometric dance, following the contours of space-time without complaint. Einstein wrote down a set of field equations, 10 interlocking differential equations really, that describe how mass energy and the curvature of space-time balance each other. They're the universe's rules of accounting, and like any good ledger, they have to stay balanced on both sides. Within months of Einstein publishing these equations, a German physicist named Karl Schwarzschild, serving on the Russian front during World War I, found an exact solution. He considered the simplest possible case, a perfectly spherical, non-rotating mass sitting alone in space. What does space-time look like around such an object? Schwarzschild worked through the math and delivered a precise description. For most purposes, far from the mass, everything looked normal. Planets would orbit just as Newton predicted. Light would curve slightly, nothing alarming. But as you moved closer, something strange appeared in the equations. There was a particular radius, now called the Schwarzschild radius, where certain mathematical terms went to infinity. The geometry seemed to break down, at least on paper. For a mass like the Sun, this radius was about 3 kilometres. For Earth, less than a centimetre. These numbers seemed absurdly small, far smaller than any real object could be squeezed. So for decades, physicists treated the Schwarzschild radius as a mathematical artifact, a quirk of the coordinate system, perhaps a sign that the equations needed different variables or a better interpretation. It was filed as a minor anomaly, not a physical thing you'd actually encounter. But stars, as it turns out, don't live forever. They spend most of their existence in a stable balance. Nuclear fusion in their cores produces outward pressure that holds them up against the relentless inward pull of their own gravity. It's a truce that can last billions of years. Eventually, though, the fuel runs out. For stars like our Sun, the end is relatively gentle. The core contracts into a white dwarf, a dense ember about the size of Earth, supported by what's called electron degeneracy pressure. a quantum mechanical effect that keeps electrons from being squeezed too close together. For more massive stars, the core can collapse further, crushing atoms until protons and electrons merge into neutrons, forming a neutron star, a city-sized sphere with the mass of a sun, held up by neutron degeneracy pressure. These are extreme objects, but they're still objects in a traditional sense. They have surfaces, structures, a kind of solidity. In the 1930s, an Indian astrophysicist named Subramanian Chandrasekhar calculated that there's a limit to how much mass a white dwarf can hold, about 1.4 solar masses. Beyond that, electron pressure simply isn't enough. A similar limit exists for neutron stars, somewhere around 2 to 3 solar masses, though the exact number is still debated because we don't fully understand how matter behaves at such densities. The troubling implication was clear. If a stellar core is massive enough when it collapses, there's no known force that can stop gravity from continuing to compress it. No pressure, no quantum effect. Nothing in the standard physics toolkit can hold it up. The equation suggested that such a core would just keep collapsing, shrinking past the size of a neutron star, past any conventional stopping point, until it reached that problematic Schwarzschild radius, and perhaps beyond. This was deeply uncomfortable for many physicists. Surely nature had some mechanism, some last-minute reprieve that would prevent such an extreme outcome. Surely the universe wouldn't allow something so singular, so pathological. But the math kept leading in the same direction. By the middle of the 20th century, physicists like J. Robert Oppenheimer and his students were working through the details of gravitational collapse, following the equations past the point where intuition gave out. What they found was that once an object collapsed within its Schwarzschild radius, it formed a one-way boundary in space-time. Cross that boundary going inward, and you could never return or even send a signal back out, not without travelling faster than light, which relativity forbids. The terminology was awkward at first. People spoke of gravitationally completely collapsed objects, or frozen stars, because from the outside time dilation made it appear that anything falling toward this boundary would slow down and freeze just above it. But in the 1960s, the physicist John Wheeler popularised the term black hole, and it stuck. The name was slightly misleading. There's no actual hole, no tear in space-time, just a region where the geometry has become so steep that escape is impossible, but it was vivid, simple, and far easier to say than the alternatives. Once the label was in place, the concept became a file folder you could point to, discuss, refine. It made the uncomfortable idea manageable. So what is a black hole, really, in the calmest possible terms? It has two main features. First, the event horizon. This is the one-way boundary at the Schwarzschild radius. It's not a physical surface, there's no wall, no membrane. If you were falling through it, you wouldn't feel anything special at the moment of crossing. Locally, space-time is smooth. But from that point on, every path you could take, every possible future trajectory, leads inward. The geometry has tilted so steeply that inward is as inevitable as forward in time. Second, the singularity. Somewhere at the centre, the equations predict a point of infinite density and curvature. This is almost certainly a sign that general relativity is incomplete, that we need a theory of quantum gravity to describe what really happens there. But from the outside, it doesn't matter much. The horizon is the boundary that controls what we can observe and interact with. To an observer far away, anything approaching a black hole appears to slow down, redden, and fade, taking an infinite amount of time to actually cross the horizon. To the infalling object, time passes normally, and the crossing happens in finite proper time. It's just space-time following the rules, even when those rules become deeply strange. If black holes are invisible by definition, how do astronomers find them? They look for the effects. One of the earliest and most reliable methods involves binary star systems. Imagine a normal star orbiting an invisible companion. Gas from the star can spill over and spiral toward the unseen object, forming a disk of material that heats up through friction and magnetic interactions. As this gas accelerates and compresses, it reaches temperatures of millions of degrees and emits X-rays. Telescopes detect these X-ray sources, and by measuring the orbit of the visible star, how fast it moves, the period of its orbit, astronomers can calculate the mass of the invisible companion using straightforward Newtonian mechanics. If that mass exceeds the limits for white dwarfs and neutron stars, and there's no other plausible explanation, you've quietly identified a stellar mass black hole. Cygnus X1 was one of the first such cases, flagged in the early 1970s. No dramatic visuals, just a persistent X-ray signal and careful orbital data pointing to something compact and massive that couldn't be anything else. The centres of galaxies provided another, even more striking ledger entry. For decades, astronomers noticed that stars near the cores of many galaxies moved surprisingly fast, as if they were orbiting something enormous but invisible. In our own Milky Way, careful observations tracked individual stars looping around an apparently empty point called Sagittarius A. By plotting their positions year after year, astronomers traced full orbits for some of these stars, measuring periods and speeds with increasing precision. The math is simple. Orbital dynamics tell you the mass enclosed within the orbit. For Sagittarius A, the numbers pointed to about 4 million solar masses packed into a region smaller than our solar system. There's no conventional cluster of stars or gas cloud that could be that compact and that massive without collapsing or producing light. The only explanation that fits the data is a supermassive black hole, sitting quietly at the galaxy's centre, organising the motions of stars around it like a heavy bookend holding up a long shelf. Light itself offers clues through gravitational lensing. When light from a distant galaxy passes near a massive object on its way to us, the curved spacetime bends the light's path, splitting the background source into multiple images or arcs. This is how spacetime acts as a lens, and the distortion pattern depends on the mass and distribution of the lensing object. Sometimes these patterns hint at compact, massive concentrations along the line of sight, and occasionally those turn out to be black holes, either isolated or at the centres of galaxies. The evidence arrives as careful measurements of brightness, position, and shape, cross-checked against models of mass distribution. It's detective. Work conducted with photon counts and sky coordinates, more ledger entries than spectacle. Then there are gravitational waves. According to general relativity, accelerating masses produce ripples in spacetime itself, spreading outward at the speed of light. These ripples are extraordinarily faint. Even violent cosmic events produce distortions measurable only in billionths of a metre. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first confirmed gravitational wave signal. The source was two black holes, each about 30 times the mass of the Sun, spiralling into each other and merging. The signal lasted a fraction of a second, a brief rising chirp in the data as the black holes circled faster and faster before coalescing. That chirp encoded their masses, their spins, their distance from us. It was cosmic drama recorded not as a movie, but as a clean, tidy signature on a graph. Since then, dozens more black hole mergers have been detected, each one adding a precise entry to our catalogue of these objects, and confirming that binary black holes exist, that they merge, and that spacetime really does ripple when massive objects accelerate. Most of the light we associate with black holes doesn't come from the black hole itself, of course. It comes from the accretion disk, the swirling mass of gas and dust that spirals inward. Material doesn't fall straight in because it usually has some angular momentum, some sideways motion. Instead, it settles into a flattened disk, orbiting faster as it moves closer, heating up through friction and compression. Magnetic fields threading the disk can extract energy and launch powerful jets perpendicular to the disk, carrying matter and radiation away at near-light speeds. This is how quasars work. Supermassive black holes at the centres of distant galaxies, actively feeding, producing more light than entire galaxies of stars. From our perspective, billions of light years away, these appear as bright points that outshine everything around them. The black hole itself remains dark, a silent consumer at the centre, but the infalling material writes a brilliant entry in the sky's ledger, visible across most of the observable universe. It's now understood that supermassive black holes, millions to billions of solar masses, reside at the centres of most large galaxies. They're not the dominant mass of the galaxy. The stars and dark matter far outweigh them. But they occupy a central position, both literally and organisationally. Their gravity shapes the orbits of nearby stars. Episodes of active accretion can drive powerful outflows that heat or expel gas from the galaxy, potentially regulating star formation. Over cosmic time, these central masses grow through mergers with other black holes and by gradually accreting gas. They're like heavy bookends. Not the entire library, but stabilizing presences that quietly influence how everything else arranges itself over billions of years. Imaging a black hole directly is a challenge, because by definition the object itself emits no light. What you can image is the shadow it casts against a glowing background. In 2019, the Event Horizon Telescope collaboration released the first such image, showing the supermassive black hole at the centre of the galaxy M87. The technique involved linking radio telescopes across the globe, from Hawaii to Chile to the South Pole, creating an effective dish the size of Earth. Each telescope recorded data, and later those data streams were carefully synchronized and combined using sophisticated algorithms. The result was an image of the black hole's shadow, a dark circle surrounded by a bright asymmetric ring of emission from the accretion flow. It wasn't a photograph in the traditional sense. It was a reconstruction, a detailed report built from millions of measurements, hours of observation, and patient computation. In 2022, they released a similar image of Sagittarius AI, our own galaxy's central black hole. Both images confirmed the predictions of general relativity in extreme conditions and provided direct visual evidence of the event horizon scale. In 1974, Stephen Hawking introduced a surprising twist. When you account for quantum field theory near the event horizon, black holes aren't entirely black. Pairs of virtual particles constantly pop into and out of existence everywhere in space, normally annihilating each other almost immediately. But near the horizon, one particle of a pair might fall in while the other escapes. From a distant observer's perspective, this looks like the black hole emitting radiation, as if it has a temperature. The effect is called Hawking radiation, and the temperature is inversely proportional to the black hole's mass. For a stellar mass black hole, that temperature is a tiny fraction of a degree above absolute zero, far colder than the cosmic microwave background, so in practice such black holes absorb more radiation than they emit. For supermassive black holes, the temperature is even lower. Only very small black holes, if they exist, would radiate significantly. Over unimaginably long timescales, far longer than the current age of the universe, a black hole left alone would slowly evaporate, shrinking as it radiates away its mass. It's less an immediate concern and more a note about long-term archival policy. Even black holes, given enough time, may not be permanent. Hawking radiation introduced a puzzle called the information paradox. Quantum mechanics says that information about the physical state of a system should never be truly destroyed. It can be scrambled or hidden, but in principle, it should always be recoverable. Classical black holes, however, seem to erase information. Everything that falls past the horizon is lost to the outside universe, hidden behind a one-way boundary. If the black hole then evaporates into featureless thermal radiation, where did the information about what fell in go? This tension between quantum mechanics and general relativity has prompted decades of theoretical work. Some proposals suggest information is stored on the event horizon in a holographic way, encoded in subtle correlations in the outgoing Hawking radiation. Others invoke exotic ideas like firewalls, quantum entanglement across the horizon, or new physics at the singularity. For now, the universe continues operating smoothly while theorists debate the correct filing protocol. It's a disagreement about how the records are kept, not whether they exist. There are more speculative entries in the black hole file. Primordial black holes, for instance, might have formed in the extremely early universe from density fluctuations, before stars even existed. If they exist, they could range from tiny masses to stellar scale, and might even contribute to dark matter. Microscopic black holes could theoretically form in high-energy particle collisions, though none have been observed, and current theories suggest they'd evaporate almost instantly via Hawking radiation. Wormholes, hypothetical tunnels connecting distant regions of spacetime, are often confused with black holes in popular media, but they're different solutions to Einstein's equations, generally requiring exotic matter with negative energy density to remain stable, and there's no evidence they exist in nature. Most of the practical cosmic bookkeeping is done by ordinary stellar mass and supermassive black holes, behaving in measurable, predictable ways. The rotation of black holes adds another layer to the filing system. Real black holes aren't perfectly static spheres like Schwarzschild imagined. They spin, sometimes rapidly, because the matter that collapsed to form them carried angular momentum. A rotating black hole drags space-time around with it, creating a region called the ergosphere just outside the event horizon, where nothing can remain stationary. not even light. This effect, frame dragging, means that spacetime itself is rotating, and anything in that region gets swept along like a stick caught in a whirlpool. The mathematics describing rotating black holes comes from a solution found by Roy Kerr in 1963, and it reveals structures more complex than the simple Schwarzschild case. The event horizon is still there, but its shape and properties depend on how fast the black hole spins. Theoretical calculations suggest you could extract energy from the ergosphere, a process called the Penrose mechanism, where carefully aimed particles or waves could steal some of the black hole's rotational energy. In practice, magnetic fields threading the accretion disk might accomplish something similar, powering the intense jets seen in active galactic nuclei. The universe, it turns out, has built-in mechanisms for recycling energy, even from objects designed to trap everything. Binary black hole systems offer particularly clean laboratories for testing general relativity. When two black holes orbit each other, they lose energy by radiating gravitational waves, causing their orbit to gradually shrink. As they spiral closer, the orbital period decreases and the gravitational wave signal increases in frequency and amplitude, producing that characteristic chirp. In the final moments before merger, the black holes are orbiting each other many times per second, moving at a significant fraction of light speed, deep in each other's warped spacetime. The resulting waveform encodes detailed information about the masses and spins of both objects, the orientation of their orbit, and the properties of the final merged black hole. By comparing observed signals to theoretical templates computed from Einstein's equations, physicists can test whether general relativity accurately describes gravity in these extreme regimes. So far, the agreement is excellent. The universe follows the rules even when two of its heaviest objects collide at relativistic speeds. There's also the matter of intermediate mass black holes, a category that's proven surprisingly elusive. We have good evidence for stellar mass black holes, a few to a few dozen solar masses, formed from collapsing stars, and supermassive black holes millions to billions of times heavier. But black holes in between, perhaps a few hundred to a few 100,000 solar masses, have been harder to confirm. Some globular clusters and dwarf galaxies show hints of them, but the evidence is less definitive than for their smaller and larger cousins. Gravitational wave detections have started filling in this gap, with a few merger events pointing to black holes in the lower end of the intermediate range. How supermassive black holes grow so large so quickly in the early universe remains an open question, and intermediate mass black holes might be part of the answer, serving as seeds that merge and accrete gas over cosmic time. It's a missing piece of the evolutionary story, a gap in the ledger that observers are working to close. The interaction between black holes and their host galaxies forms a feedback loop that appears crucial to galaxy evolution. When a supermassive black hole actively accretes gas, the resulting energy output, radiation and jets, can heat or push away nearby gas, suppressing star formation. This prevents the galaxy from converting all its gas into stars too quickly, and may explain why the most massive galaxies have relatively old stellar populations. Conversely, when gas cools and falls toward the centre, it can fuel the black hole, triggering another episode of activity. Over billions of years, this cycle regulates both the growth of the black hole and the star formation rate of the galaxy. Observations show a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy's bulge, suggesting the two grow together in a coordinated way. The black hole is not just a passive resident, but an active participant in shaping its galactic environment, an administrative centre whose activity influences the entire institution. Tidal disruption events provide another window into black hole behaviour. Occasionally, a star wanders too close to a black hole, close enough that the difference in gravitational pull between the star's near and far sides becomes extreme. This tidal force stretches and tears the star apart, a process called spaghettification, which sounds dramatic but is really just differential gravity doing what differential gravity does. Some of the stellar debris falls into the black hole, producing a bright flare of radiation as it heats up in the accretion process. These flares can last months to years and have distinct observational signatures, a sudden brightening in a previously quiet galactic nucleus, followed by a gradual fade. Each event offers a chance to study how matter behaves in the final moments before crossing the horizon and to measure properties of the black hole from the light curve and spectrum of the disrupted material. They're rare, but ongoing sky surveys are catching more of them, adding yet another category to the observational files. The future of black hole astronomy looks toward even more sensitive gravitational wave detectors, both ground-based upgrades to LIGO and future space-based observatories like LISA, which will detect lower frequency waves from merging supermassive black holes across cosmic distances. Next-generation radio telescopes and continued observations with the Event Horizon Telescope will refine our images of black hole shadows and test general relativity with increasing precision. Multi-messenger astronomy, combining gravitational waves, electromagnetic observations, and possibly neutrinos, will provide richer datasets for understanding the environments around black holes and the mechanics of matter under extreme conditions. Each advance adds detail to the portrait, sharpens the entries in the ledger, and occasionally surprises us with phenomena we hadn't anticipated. The universe remains an orderly place, but the order is subtle, and we're still learning to read it. So here we are at the end of the audit. Black holes began as a speculative calculation about dark stars in the 1700s, matured into a mathematical oddity in the early 20th century, and gradually earned a place as one of the fundamental structures of the universe. They're endpoints for massive stars, organizational centers for galaxies, sources of the most energetic phenomena we observe, and testing grounds for our deepest theories about spacetime and quantum mechanics. They're not monsters or cosmic vacuum cleaners. They don't roam around devouring everything in sight. They're simply regions where gravity, following the rules to their logical conclusion, has created a one-way boundary in spacetime. They record the history of collapsed stars, merged galaxies, long epochs of accreting gas. They shape the orbits of nearby matter. Occasionally they announce a merger with a brief gravitational wave signature, a quiet ping in our detectors. To a sleepy listener, they're less menacing and more like heavy, silent filing cabinets in the cosmic office, places where the universe sets aside material it's finished rearranging. We've learned to read the labels, check the contents indirectly, and slowly map the filing system. The paperwork is mostly in order, even if some of the deeper drawers remain locked. Good night. The next story is about to begin. Please relax and enjoy. The rain taps against the window of the small observatory control room, each drop catching the glow of monitor screens before sliding into darkness. Sarah watches the telemetry scroll past, numbers that represent a spacecraft sitting in nothing, balanced on the edge of falling forever. She's been awake for 36 hours straight, shepherding the telescope through its final approach to a point in space that doesn't really exist. Not as a place you could touch or see, just a sweet spot where the mathematics of motion allows a machine to hover without effort, almost. The coffee has gone cold again. Outside, the storm moves across the desert in grey sheets, obscuring the mountains. Inside, the room hums with the steady breath of computers translating signals that left the spacecraft 28 seconds ago, travelling at the speed of light across 1,000,000 miles of emptiness. 28 seconds is an eternity when you're trying to thread a needle with a robot the size of a bus. Approaching orbital insertion corridor, calls Marcus from the navigation console. His voice carries the careful neutrality of someone who's done this dance before, who knows that excitement leads to mistakes. Sarah nods, her fingers hovering over the command sequence that will fire the thrusters for exactly 17 seconds, nudging their telescope onto a loop around an invisible point that exists only in the language of gravity and spin. The Lagrange points aren't parking lots in any ordinary sense. They're more like those moments in a spinning top's wobble, where it seems to hang suspended, neither rising nor falling, caught in a negotiation between forces that should tear it apart. Between any two bodies locked in gravity's embrace, the Sun and Earth, Earth and Moon, a planet and its satellite, there exist 5 such moments frozen in space, 5 places where a smaller object can keep pace with the larger body's dance, without constantly burning fuel to stay in position. Sarah thinks of them as harbours, though that's probably too solid a word for what they really are. Harbours suggest docks and moorings, something you can tie yourself to. These are more like the eye of a hurricane, calm centres in a rotating storm of gravitational forces. You can rest there, but never truly relax. The universe is always trying to push you out, gently but insistently, and you have to keep correcting, keep adjusting. Tiny burns of hydrazine or pulses of ion thrust, whispers of force that add up to staying put. The one they're heading for sits 1,000,000 miles from Earth, directly opposite the Sun. From that vantage, the Earth, Moon, and Sun all cluster together in one direction, leaving the rest of the sky dark and cold and perfect for looking outward into the deep night where galaxies sprawl like spilled salt across black cloth. This is L2, the second Lagrange point of the Sun-Earth system, and it's where humanity parks its most ambitious eyes. She remembers learning about orbits as a child, the simple picture of objects falling around Earth in neat circles. Later came the complication. Orbits are always falling, but falling sideways fast enough that the ground keeps curving away beneath you. You're perpetually missing the planet, threading the needle between escape and impact. But in a frame of reference that rotates with two bodies, say, a coordinate system that spins with the Earth as it circles the Sun, something strange happens. The centrifugal effects that emerge from that rotation add to the gravitational pulls in ways that create these 5 special regions where everything balances just so. Not balanced like a ball on flat ground, stable and happy. More like a marble balanced on top of a beach ball, possible in theory, requiring constant attention in practice. Well, 3 of them anyway. L1, L2 and L3 are unstable saddle points, ridges you can perch on if you're careful. L4 and L5, the points that form equilateral triangles with the two bodies, are different. They're shallow bowls where objects can settle into lazy orbits, following tadpole or horseshoe paths that loop around the point without drifting away. Jupiter has thousands of asteroids lounging in its L4 and L5 points, fossil remnants from the solar system's formation, trapped in those gentle gravitational valleys. Burn sequence armed, Sarah says, and her voice sounds far away even to herself. This is the culmination of 8 years of design, 3 years of construction, 2 years of testing, and 6 months of travel. The telescope cost more than a small nation's GDP, carries instruments that can see wavelengths of light the human eye never evolved to detect, and right now depends entirely on 17 seconds of controlled fire. Marcus counts down. Mark in 10, 9, 8. The spacecraft doesn't actually sit on the point itself. That would be like trying to balance a pencil on its tip. Theoretically possible, practically absurd. Instead, it traces what they call a halo orbit, a 3-dimensional loop that circles the invisible point like a moth around a flame, except the flame isn't there and the moth is solar-powered and following equations that would have made Newton weep with joy. These orbits rise above and dip below the plane of Earth's orbit around the Sun, keeping the spacecraft in constant sunlight for its solar panels, while maintaining a clear view of both Earth for communications and deep space for science. 3, 2, 1, burn. The telemetry stutters, updates. The velocity vector shifts infinitesimally on her screen, rotating the spacecraft's trajectory from an approach hyperbola into the first graceful arc of its permanent waltz. Sarah holds her breath without meaning to, watches the numbers settle into their predicted ranges, green lights cascading down the status board like a slow waterfall of confirmation. Capture confirmed, Marcus announces, and the tension breaks like glass. Someone cheers in the back of the room, Sarah allows. Herself a smile, small and private, the kind you wear when you've just parked a billion-dollar machine in a spot that exists only as a solution to differential equations. The point they've reached has a strange property. From here, the Sun is always in the same direction, and so is Earth. The spacecraft's sun shield, a tennis court-sized structure of layered captain and aluminum, unfolded 2 weeks ago in a process that took 6 hours and aged Sarah 5 years, can block all 3 sources of heat at once. Behind that shield, in permanent shadow, the telescope's instruments will cool to just a few degrees above absolute zero, cold enough that their own heat won't swamp the faint infrared whispers from galaxies born when the universe was young. At Sun-Earth L1, a different class of spacecraft keeps watch. That point sits between Earth and Sun, upstream in the solar wind, and the machines there stare at the Sun's roiling surface, watching for eruptions that could damage satellites or power grids. They're sentinels, giving Earth anywhere from 15 minutes to an hour of warning when a coronal mass ejection comes howling outward at 1,000,000 miles per hour. From L1, you see the Sun's face clearly and constantly. No eclipses, no interruptions, just endless vigil. L3 sits opposite Earth on the far side of the Sun, and it's the least useful of the group. Too dynamically unstable, too expensive to reach, too difficult to communicate with when the Sun sits between you and your spacecraft for weeks at a time. Science fiction writers sometimes park secret planets there, hidden Earths riding our own orbit but forever out of sight behind the sun's bulk. In reality, perturbations from other planets would reveal such a world quickly, and we've looked anyway, just to be sure. There's nothing there but empty space and unused potential. The Earth-Moon system has its own Lagrange points, closer to home and more immediately useful. EML1, sitting between Earth and Moon, serves as a conceptual gateway for missions heading to or from the lunar surface. EML2, beyond the Moon's far side, offers something more interesting. A place where a communications relay can hover, maintaining constant line of sight with both Earth and the Moon's hidden face, that hemisphere that always turns away from us, perpetually shy. Sarah watches the telescope begin its first science observations, cameras and spectrometers waking from cruise mode like a sleeper stretching after a long journey. The targets are prosaic at first, calibration stars, objects whose properties are well known, used to verify that the optics survived the voyage, and the cryocoolers are working as designed. Later will come the real work, staring at patches of apparently empty sky for days at a time, collecting photons that left their sources when the universe was a fraction of its current age, light that's been travelling for most of cosmic history to reach this particular arrangement of mirrors and detectors. Station keeping will become routine, she knows. Every few weeks the flight dynamics team will calculate a small correction burn, a few meters per second of delta V to nudge the spacecraft back onto its nominal path. Solar radiation pressure, literal photons pushing on the sunshield, will perturb the orbit. The Moon's gravity will tug irregularly. The model they use assumes two bodies, Sun and Earth, but reality includes Jupiter and Venus and Mars, all pulling in their own subtle ways, and the Earth itself isn't perfectly spherical, and the Sun's radiation pressure varies with the solar cycle. The universe is messier than the mathematics that describe it, and engineering is the art of succeeding despite that messiness. The halo orbit the telescope traces isn't circular. It's more of a lopsided oval in 3 dimensions, carefully chosen so that the spacecraft never passes through Earth's shadow. No eclipses means no thermal cycling, no batteries depleting and recharging, no stress on components designed to operate at constant cryogenic temperatures. The path keeps the sunshield properly oriented, always edge onto the sun, always blocking the view of Earth and Moon, maintaining that precious darkness behind which the telescope peers into deep time. Other spacecraft have called L2 home before this one. Early missions mapped the cosmic microwave background from here, measuring the afterglow of the Big Bang with exquisite precision, finding patterns in that ancient light that revealed the universe's composition and fate. Their data rewrote cosmology, turned speculation into measurement, answered questions humans had been asking since we first looked up, and wondered what all those lights meant. Sarah remembers studying those missions in graduate school, learning how they stabilized their orbits, how they calibrated their instruments, how they dealt with the slow accumulation of energetic particles that space hurls at anything that ventures beyond Earth's magnetic shield. L2 sits outside that protection, exposed to the solar wind and cosmic rays, and every spacecraft that goes there must armour itself accordingly, shielding its electronics and accepting that eventually radiation damage will end the mission. The advantages outweigh the risks. At L2, the thermal environment is predictable. Stable temperatures make for stable measurements, and stable measurements make for good science. The lighting is constant, which simplifies power management. Communications with Earth are straightforward. No occultations, no periods of enforced silence, and most importantly, the view is unobstructed. No warm Earth glowing in infrared, drowning out the faint signals from distant galaxies. Just cold darkness and patient observation. The engineering required to make it all work fascinates her in ways she doesn't fully understand herself. The sunshield unfolds like origami in reverse, layer after carefully designed layer, each one blocking a portion of the sun's heat, so that the final layer, closest to the telescope, reaches temperatures cold enough to freeze air solid. Attitude control keeps everything aligned, reaction wheels spinning to maintain orientation, momentum dumped occasionally by firing thrusters, a constant juggling act of angular momentum and propellant budgets. At L1, the engineering priorities differ. Spacecraft there face the sun directly, deliberately, instruments drinking in the light and radiation to monitor solar activity. They need different shields, different orientations, different orbits chosen to keep communications with Earth open, while staring into that nuclear furnace 93 million miles away. But the basic principle remains the same. Find the sweet spot, trace a loop around it, and nudge yourself back on course when you drift. The science that flows from these harbours transforms astronomy. Space weather predictions improve with better solar monitoring from L1. Exoplanet hunters use infrared telescopes at L2 to watch stars for the tiny dips in brightness when worlds transit their faces. Studies of star formation peer into dust clouds that visible light can't penetrate, seeing protostars ignite in their cocoons, and cosmologists map the structure of the universe itself, galaxy by galaxy, building three-dimensional charts of matter's distribution across billions of light years. Marcus brings her another coffee, this one actually hot. "First light looks good," he says, and she nods, scrolling through spectra that mean nothing to her, but everything to the astronomers who will spend years analysing them. The data begins its journey earthward, packets of ones and zeros riding radio waves across the Gulf, arriving 28 seconds after they're sent, accumulating in storage arrays where scientists will sift through them like prospectors panning for gold. She thinks about the misconceptions, the questions journalists always ask when trying to explain these missions to the public. No, there's no gravity-free zone. Gravity is everywhere. It's the whole reason the Lagrange points exist. No, the spacecraft doesn't anchor to anything physical. There's no there, just a location where forces balance. And no, maintaining position doesn't require huge amounts of fuel, just tiny corrections, teaspoons of thrust spread over months and years, enough to counteract the slow drift that perturbations impose. The restricted three-body problem that yields these points is an approximation, she knows. Reality includes every massive object in the solar system, all pulling and pushing in their own ways. The sun isn't perfectly spherical. The Earth and Moon don't orbit in a perfect plane. Solar radiation pressure varies, but the Lagrange framework remains useful because it captures the essential dynamics, provides a map that's accurate enough for navigation even if it's not perfectly true. All models are wrong. Some are useful. Looking ahead, she imagines future missions, fuel depots at EML1, staging points for lunar sorties and Mars missions, fleets of telescopes at L2, working in concert to achieve baselines impossible for any single instrument, communications relays at Earth-Moon L4 and L5, providing constant coverage of cislunar space, sample return missions using the Earth-Moon Lagrange points as waypoints, dropping off precious cargo before diving back toward the Moon or beyond, autonomous platforms that ride the weak stability boundaries, those gravitational manifolds that connect different Lagrange points, allowing nearly propellantless transfers if you're patient and clever about timing. Other worlds have their own Lagrange points, 5 accompanying every two-body partnership. Mars and the Sun, Jupiter and the Sun, where Trojan asteroids swarm by the thousand, even small asteroid moons create miniature versions of these same patterns. Wherever two objects dance in mutual orbit, the 5 notches appear, inevitable consequences of gravity and rotation. The rain has stopped, she realizes. Dawn lightens the eastern sky, and the desert emerges from shadow, brown and grey and beautiful in its austerity. Sarah stretches, joints popping, exhaustion finally catching up now that the critical phase is over. The telescope will orbit its invisible point for years, maybe a decade if the cryocoolers and electronics hold out, staring into darkness and finding light. She leaves Marcus to monitor the routine observations and steps outside, breathing air that smells of wet creosote and ozone. 1,000,000 miles away, a machine she helped design traces its loop around a point that exists only in mathematics, a harbour made of timing and geometry and tiny patient burns. It's not falling, and it's not floating. It's balanced in motion, perpetually catching up to two worlds that themselves never stop moving. Above her, invisible in the brightening sky, Earth continues its ancient orbit, and at 5 specific places in that orbit's geometry, spaces exist where humans have learned to park their ambitions, their curiosity, their hunger to see what the universe looks like from somewhere other than the bottom of a gravity well. The Lagrange points aren't destinations exactly. They're vantages, perches, quiet corners in a cosmos that never stops wheeling. Sarah thinks about all the light streaming toward that telescope right now, photons that began their journey before Earth existed, before the sun ignited, before anything but hydrogen and helium and darkness filled the universe. That light will arrive at precisely calibrated mirrors, bounce through precisely figured optics, strike precisely cooled detectors, and become data. become knowledge, become answers to questions nobody knew how to ask when she was young. The sun clears the horizon, and she raises a hand to shade her eyes. Somewhere out there, invisible and unreachable but precisely located, a point in space waits, and a spacecraft circles it like a faithful moon around a planet that isn't. There. It will stay for years, nudged and corrected, shepherded by engineers and guided by physics, until its fuel runs low, or its instruments fail, or its mission ends because there's nothing left to discover. But that day is far away. For now, the telescope stares into the deep black, and the data flows earthward, and Sarah stands in the desert dawn, tired and satisfied, thinking about harbours that have no docks and parking spots, that exist only in the language of motion and force. The universe keeps turning, and we've learned to find the still points in that turning, the places where we can rest, not forever, but long enough to see what needs seeing, to measure what needs measuring, to understand just a little more about this strange and beautiful cosmos we inhabit. She walks the perimeter of the facility, letting her mind drift the way it does when exhaustion becomes something close to meditation. The gravel crunches under her boots, and she notices details she normally wouldn't. The way the morning light catches on quartz fragments, the tracks of some nocturnal creature that crossed the path while she was inside watching numbers, the distant call of a hawk beginning its hunt. It occurs to her that she's been so focused on the far that she's forgotten the near, that the same physics that governs spacecraft also governs hawks and stones, and the way morning spreads across a desert. Inside, the team will be settling into the rhythm of operations, the long, slow dance of maintaining a mission that measures its objectives in years rather than days. There will be anomalies to investigate, software patches to upload, science proposals to evaluate, budget meetings and status reports and all the mundane machinery that keeps a spacecraft functioning across 1,000,000 miles of nothing. But right now, in this particular moment between the crisis of insertion and the routine of operations, there's a pause, a breath, a space where she can think about what they've actually accomplished. The transfer from Earth to L2 took 6 months, but it wasn't a straight line. Nothing in orbital mechanics ever is. The spacecraft followed what the navigators call a trajectory arc, spiralling outward from Earth's gravitational influence, while the sun's pull gradually took over as the dominant force. They fired the engines in carefully timed bursts, each burn calculated months in advance but adjusted in real time based on tracking data, nudging the path until it intersected with the halo orbit at just the right angle and velocity. Too fast and the spacecraft would overshoot, sailing past the point into the solar system's depths. Too slow, and it would fall back toward Earth, wasting fuel and time in a second attempt. Sarah had dreamed about those burns, literally dreamed about them in the weeks leading up to each maneuver. In her dreams, the numbers were always wrong, the velocity vectors pointing in impossible directions, the spacecraft tumbling uncontrolled while she watched helplessly from her console. She knows enough about psychology to recognize anxiety expressing itself in the language of her profession, but knowing doesn't make the dreams any less vivid or the relief of success any less sweet. The concept of weak stability boundaries fascinates her more than it probably should. These are regions of space where the gravitational influences of multiple bodies create channels, invisible highways that a spacecraft can follow with minimal propellant expenditure. They're related to the Lagrange points, but more extensive, forming networks that connect different parts of the solar system in ways that aren't obvious from simple two-body orbital mechanics. Some missions have used these pathways to reach the moon or asteroids, trading time for fuel, taking months or years to coast along these gravitational rivers, rather than burning directly to their destinations. She imagines a future where spacecraft routinely use these manifolds, hopping from one Lagrange point to another like stones across a stream, building up speed or changing direction by carefully timing their passages through each point's sphere of influence. It would require patience and precision, but both are cheaper than propellant when you're trying to move large masses across interplanetary distances. Fuel depots at the Lagrange points could serve these travellers, autonomous stations dispensing hydrazine or xenon to spacecraft that need a top-up before continuing their journeys. The Earth-Moon L4 and L5 points remain largely unused despite their stability. They sit 60 degrees ahead of and behind the Moon in its orbit around Earth, forming equilateral triangles with the Earth and Moon at the other two corners. Unlike L1, L2 and L3, which require constant correction to maintain, L4 and L5 are gravitationally stable, at least stable enough that small objects can linger there for thousands or millions of years without much perturbation. Earth has at least one confirmed Trojan asteroid at L4, a small rock designated 2010 TK7 that traces a complex path around the point, neither approaching nor receding, caught in the gravity well like a marble rolling around the rim of a bowl. Some proposals suggest placing communication satellites at Earth-Moon L4 and L5, creating a permanent infrastructure for cislunar operations. From those vantage points, you could see both Earth and Moon simultaneously, providing continuous coverage of the lunar surface, including the poles, where permanent shadow holds deposits of water ice that future missions might harvest for propellant and life support. The geometry is elegant. 5 points, 3 of them unstable ridges, 2 of them stable valleys, all of them useful in different ways, all of them consequences of the same fundamental physics. Sarah wonders what Lagrange himself would think of the uses we've found for his mathematical curiosities. Joseph Louis Lagrange worked out the 5-point solution in 1772 while studying the three-body problem, how 3 mutually attracting masses move under their own gravitation. It was pure mathematics to him, an interesting puzzle in celestial mechanics with no obvious practical application. He couldn't have imagined spacecraft, or that humans would someday need parking spots in space, or that his equations would guide machines carrying instruments that could detect light from the universe's childhood. That's the way of mathematics, she supposes. You discover patterns and relationships because they're interesting, because they satisfy some aesthetic sense of order and beauty, and only later, sometimes centuries later, does someone find a use for them. Number theory was recreational mathematics for thousands of years before modern cryptography made it the foundation of digital security. Calculus was Newton and Leibniz playing with infinitesimals before it became the language of physics and engineering. And Lagrange's 5 points were curiosities before they became addresses. Marcus appears in the doorway, squinting against the brightening sky. "You should get some sleep," he says, and it's not a suggestion so much as an observation of obvious fact. Sarah nods but doesn't move immediately. She's reluctant to leave, even though the critical phase is over, and there's nothing she can do now that the automated systems can't handle better. There's a possessiveness that comes with working on a mission for years, a feeling that the spacecraft is somehow hers, that she needs to watch over it personally. It's irrational, but she's learned that most feelings about space missions are. "How's the thermal balance?" she asks, because she can't quite let go yet. Marcus smiles, recognizing the delay tactic. Within nominal range, the sunshield is performing exactly as modelled. Cold side holding at 47 Kelvin, warm side at 300. The cryocoolers are cycling normally. Everything's fine, Sarah. The spacecraft doesn't need you staring at it to keep working. She knows he's right, but the knowledge doesn't make leaving any easier. This is the paradox of automation. The better the systems work, the less necessary humans become, but that doesn't stop humans from feeling responsible. They've designed autonomy into every aspect of the mission. Fault protection routines that can diagnose and respond to problems without waiting for commands from Earth. Science scheduling algorithms that optimize observations based on current conditions. Even the station-keeping burns can be triggered automatically if the orbit determination software detects excessive drift. The spacecraft could, in theory, operate for months without human intervention. But theory and practice are different countries, and humans excel at handling the unexpected. The edge cases that no algorithm anticipated. So there's always someone watching, always someone ready to intervene if the automation makes a choice that seems wrong or dangerous. It's a strange partnership, humans and machines collaborating across 1,000,000 miles of vacuum, each doing what they do best, trusting each other to handle their respective domains of expertise. Sarah finally allows Marcus to guide her back inside through the control room where the night shift is handing over to the day shift, through hallways that smell of coffee and electronics, and the particular staleness that comes from buildings where the windows never open, to the small apartment the facility provides for operations personnel during critical phases. She falls asleep within minutes of lying down, her dreams mercifully empty of tumbling spacecraft and incorrect velocity vectors. When she wakes, it's mid-afternoon, and the light through the window is harsh and bright. She checks her phone before doing anything else, looking for alerts, anomalies, anything that might require her attention. There's nothing urgent, just the routine status updates that accumulate when a spacecraft is operating normally. The telescope has completed its calibration sequence and moved on to early science observations. Some distant galaxy cluster is having its portrait taken, light from 1 billion years ago focused onto detectors that translate photons into electron counts, into digital values, into scientific understanding. She showers and dresses and makes her way back to the control room, moving through the facility with the easy familiarity of someone who's spent years in these corridors. The control room is quieter now, the urgency of insertion replaced by the steady concentration of normal operations. Fewer people at the consoles, less chatter, everyone focused on their particular subsystem or instrument. This is what most of a mission looks like. Long stretches of routine punctuated by occasional moments of interest or concern. The flight dynamics team is huddled around a monitor discussing something in low voices. Sarah drifts over, curious. They're looking at the orbit determination solution, the mathematical reconstruction of where the spacecraft actually is, based on tracking data from Earth's network of radio dishes. We're about 15 kilometers off the nominal path, one of them explains when he notices Sarah watching. Well, within tolerance. But we're planning a small correction burn for next week to tighten things up. 3 meters per second should do it. 15 kilometers sounds like a lot until you remember that the halo orbit itself is hundreds of thousands of kilometers in diameter. At this scale, 15 kilometers is like parking slightly crooked in a space large enough to hold a city. Still, precision matters in spacecraft operations, and letting small errors grow into large ones is how missions fail. Better to correct early and often, maintaining tight control even when the margins are comfortable. The burn planning process is intricate, a choreography of orbital mechanics and propellant budgets and thermal constraints. You can't just fire the thrusters. Whenever you want, the spacecraft has to be in the right orientation, the sun angles have to be acceptable, the communications link to Earth needs to be open so you can monitor the burn in real time, and you have to make sure the exhaust plume from the thrusters won't contaminate the telescope's optics or the sunshield's surfaces. Each burn requires days of preparation, checking and rechecking the calculations, simulating the maneuver in software, briefing the entire operations team on what will happen and what to do if it doesn't. Sarah finds it beautiful in its complexity, the way everything connects to everything else, how you can't change one parameter without affecting dozens of others. It's like a vast multi-dimensional puzzle where the pieces are constantly shifting, and the goal is to maintain a configuration that allows the telescope to do its science, while keeping all the subsystems healthy and the spacecraft safely parked in its invisible harbour. The engineers who designed the mission spent years thinking through these interactions, building margin into every system, anticipating failure modes and providing backup options, trying to imagine every possible problem and its solution. And yet, despite all that preparation, surprises still occur. They always do. Space is an unforgiving environment full of phenomena that don't appear in textbooks. Micrometeoroid impacts that create unexpected vibrations, solar storms that interfere with communications, cosmic rays that flip bits in computer memory, thermal gradients that cause structures to flex in ways the models didn't quite predict. Most of these anomalies are minor, solved with a software patch or an adjustment to operations procedures, but occasionally something more serious happens, and that's when the real expertise of the operations team shows itself. The ability to diagnose problems across 1 million miles of distance with limited telemetry and even more limited ability to interact with the spacecraft. Sarah has seen missions fail, has watched helplessly as spacecraft died from causes that were obvious only in retrospect. A stuck valve, a short circuit, a software bug that should have been caught in testing, small failures that cascade into total loss when you're in space and can't send a repair crew. She's learned to appreciate the fragility of these missions, how much has to go right continuously for years to achieve the science goals. Every successful observation is a small miracle of engineering persistence. The universe keeps turning while she thinks these thoughts, Earth orbiting the Sun, the Moon orbiting Earth, and at 5 invisible points in that dance, humanity maintains its tenuous presence, watching and measuring and trying to understand. The next story is about to begin. Please relax and enjoy. A lone spacecraft approaches one of Saturn's smaller shepherd moons, designation S47, a tumbling fragment barely 15 kilometers across that dances at the outer edge of the ring where ice crystals catch starlight like scattered diamonds. The mission parameters are simple. Collect samples from the ancient surface, map the gravitational anomalies that shouldn't exist in something so small, and return before the narrow launch window closes in 48 hours. But as the landing module touches down on the spongy fractured regolith, the geologist notices something impossible in the spectrometry readout. Organic compounds, complex chains that mirror the signatures detected in Enceladus's plumes 200 million kilometers away, and beneath them, a thermal gradient suggesting the moon isn't the dead rock everyone assumed. The pilot wants to leave immediately, stick to the timeline, but the geologist convinces her to deploy the deep drill. Just one borehole, and what comes up in the core sample changes everything. Layers of water ice mixed with salts and amino acids, and stranger still, microscopic chambers in the ice matrix that look almost cellular, almost purposeful. They're not alone out here, not in the way anyone expected, and the question becomes whether they're looking at contamination from Enceladus's distant fountain, or whether something about Saturn's system, the constant exchange of material between rings and moons, the electrical currents that thread through the magnetosphere, the patient stirring of tides across billions of years, has created not one place where the chemistry of life can begin, but many scattered across dozens of small worlds that brush against each other in the dark. Back on the ship, analysing the samples in the cramped laboratory, they discover the organic structures aren't quite like anything in Earth's tree of life, but they're not entirely alien either, as if the recipe is universal, but each kitchen adds its own variations, and the pilot makes the call that will end her career or make it legendary. They're not going home on schedule. They're going to spend their remaining fuel budget visiting 3 more shepherd moons, checking whether this is an isolated anomaly, or whether Saturn has been running a quiet experiment in prebiotic chemistry right under humanity's observations for 50 years. The second moon yields similar results, but the structures are more complex, almost like they've had more time to develop, and the third moon, which orbits just inside the E-ring where Enceladus's ice grains fall like snow, shows clear evidence of layered deposits, each ice fall bringing new organic material, new possibilities, building up sediments of potential over geological time. By the fourth moon, they're running on fumes and emergency reserves, and what they find isn't just chemistry anymore, but something that might be metabolism, icebound pockets where chemical gradients drive slow reactions that look almost like breathing. And the geologist realizes they're looking at the earlier stages of something profound. Not life exactly, but pre-life. The patient assembly of components in a freezer that paradoxically preserves and enables complexity, because molecules don't break down in the cold, they just wait, accumulating in higher and higher concentrations until the threshold is crossed. But there's a problem, several problems actually, starting with the fact that they no longer have enough fuel to make the journey home, and ending with the fact that Earth needs to know about this immediately, not in 5 years when the next mission arrives, because if this is happening at Saturn, then it's probably happening at Jupiter too, round Europa and Ganymede where the conditions are even better, and maybe it's happening in the Uranian system and around Triton and in the sub-ice oceans of 100 Kuiper Belt objects that haven't even been discovered yet, which means the solar system isn't mostly empty space with a few pockets of interest. It's a garden, or a laboratory, or a network of connected experiments all running in parallel. They send the data burst, compress everything they've learned into a tight beam transmission aimed at Earth, knowing it will take over an hour to arrive and years to be fully understood, and then they make the decision that nobody trains for in mission simulations. They're going to crash land on Enceladus, use the last of their fuel to match orbits with the one moon in the system that's definitely active, definitely connected to the processes they've been observing, and if they survive the landing, a long shot given that the terrain near the Tiger Stripes is fractured and unstable, they'll have front row seats to the source. The descent is controlled chaos, the ship's heat shield ablating as they punch through the thin atmosphere of ejected particles, the surface coming up fast, too fast, and the pilot pulls off a miracle, skidding across smooth ice plains before coming to rest in a field of ice boulders 3 kilometers from the nearest active vent. They have life support for 6 days, no way to launch, no rescue possible for years, but they have instruments, curiosity, and the knowledge that they're standing on the most important square meter in the solar system. The first EVA takes them to the edge of a tiger stripe, where the ice is young and blue and fractured into geometric patterns that reveal the stresses below, and they can feel the moon breathing, not metaphorically but literally, rhythmic pulses of pressure as tidal forces squeeze and release the interior, and in the cracks they see fresh ice constantly forming, crystallizing from below, bringing up dissolved minerals and organics in concentrations that make the shepherd moon samples look dilute. They collect everything they can carry, knowing each sample is irreplaceable, and as they work, the geologists start sketching a theory. What if Enceladus isn't unique? What if it's the beating heart that supplies the entire system? The plumes carrying pre-life chemistry out into the E-ring, where it gets deposited on every moon that crosses the band, seeding them all with the same starter kit, and over time, millions or billions of years, each moon develops its own variation depending on its composition, its orbit, its tidal heating, creating not separate experiments, but connected ones, a network where success on one world can propagate to others. The pilot isn't convinced, argues that the chemistry is too fragile, that radiation and vacuum would destroy anything complex before it could spread. But the geologist counters with the ice itself. Each grain is a tiny spaceship, frozen solid, protecting its cargo for the years or decades it takes to drift from moon to moon. And maybe that's exactly the timescale that matters. Not the quick chemistry of warm worlds, but the patient accumulation of cold ones. They spend days analysing samples in the ship, running every test they can improvise, and the patterns become clearer. The organic compounds aren't random, they're structured. They're selecting for stability and complexity. They're building towards something, and the question stops being whether this could lead to life and becomes how long until it does. On the 5th day, the pilot picks up a signal, faint and scattered, someone else in the system, and when they decrypt it, they discover it's a Europa mission that launched 2 years ago, just arrived, and they're seeing the same things: organic chemistry in the ice, thermal vents at the seafloor, signs of chemical gradients that look biological even if they're not. And suddenly the two crews are comparing notes across the gulf between Saturn and Jupiter, realising that they're documenting the same process at different stages, Europa further along because the ocean is deeper and warmer, Saturn still in the early phases but with more worlds participating, and together they start building the bigger picture. By the 6th day they're running out of air and out of time, and the geologist records a final message, not for the rescue mission that might come in 3 or 5 or 10 years, but for whoever finds their data cache. Keep looking at the small moons, the ones everybody ignores because they're too small to have interesting geology, too cold to have interesting chemistry, because that's where the real story is. In the quiet exchange of materials, the patient cycling of ice and organics, the way Saturn's rings act as a distribution system spreading ingredients from the active moons to the dormant ones, creating a system-wide metabolism that operates on timescales humans barely comprehend. They seal the data in a hardened capsule and place it in the ice near the ship, and then they do the only thing left. They walk out across the ice plains toward the nearest active vent, carrying their instruments, observing until the end, and as they approach the vent, the pilot notices something the geologist missed. Tiny structures in the ice around the fractures, patterns that look almost like colonies, like communities of chemical reactions that have organised themselves around the energy source. And she realises they're not just observing pre-life anymore, they're observing the threshold, the moment when chemistry becomes something else, something that responds to its environment, something that propagates, something that might, given enough time and enough moons and enough exchanges of material across the rings, become what humanity would recognise as alive. The last transmission is just coordinates and a single line. We found the garden, and it's bigger than we thought, and as the signal fades, the two crew members stand at the edge of the vent watching the plume rise kilometres into the black sky, carrying with it the raw materials of biology, spreading them across Saturn's system like seeds in a cosmic wind, and somewhere in orbit their ship's automated systems are still recording data, still measuring the flux of organics, still documenting the quiet mechanics of how worlds share their chemistry, and on Earth the first fragments of their transmission are being decoded, and teams are already planning new missions, faster ships, better instruments, because humanity has just learned that the solar system isn't a collection of isolated worlds but a connected network, a web of relationships where moons talk to each other through rings and plumes and the slow traffic of ice grains. And the question is no longer whether life exists beyond Earth, but how many different experiments are running simultaneously, how many different pathways are being explored, how many quiet gardens are growing in the cold, dark places that orbit the giant planets, waiting patiently for someone to notice them. 3 years pass before the rescue mission reaches Saturn, and in that time the data from the lost crew transforms everything humanity thought it knew about the outer solar system, not just confirming that organic chemistry is widespread, but revealing patterns that suggest the process isn't random at all. that there's something almost orchestrated about the way materials flow between worlds, the way certain shepherd moons seem to act as reservoirs while others function as mixing chambers, the way the ring system itself appears to sort particles by size and composition in ways that maximize distribution efficiency. And while nobody is suggesting intelligence or design, the mathematics of it are elegant enough to make physicists uncomfortable. The rescue ship arrives with a crew of 12, not 2, and their mission parameters have expanded exponentially. Retrieve any remains, recover all data storage, and most critically, establish a permanent research station on Enceladus, because the political and scientific consensus is that humanity can't afford to study this phenomenon in brief flybys anymore. That understanding the origin of life, or the multiple origins of life, or the continuous creation of almost life, requires patient observation measured in years, not days. They find the original ship exactly where the automated beacon said it would be, partially buried in ice accumulation, and inside the data cores are intact, filled with observations that the crew kept recording even as their oxygen ran low, detailed measurements of plume composition variations, thermal maps of the tiger stripes showing how the vents pulse in response to Saturn's tidal cycle, and most hauntingly a series of microscope images showing the progressive organization of organic compounds around energy gradients, like watching evolution in fast forward, except it's not evolution yet. It's the prelude, the sorting and testing that comes before natural selection has anything to select. They don't find bodies, not at first, but 3 kilometers away near the coordinates from the final transmission, they discover 2 suits, sealed and positioned carefully, as if the occupants simply decided to become part of the landscape they were studying. And when the recovery team opens the suits carefully, reverently, they find them filled with ice samples, dozens of vials and containers packed around the life support systems, a final act of scientific dedication that makes the rescue crew weep inside their helmets because they understand exactly what it means. These 2 people chose to turn themselves into cargo containers, to preserve one more set of irreplaceable observations, even if they couldn't survive to analyze them. The samples are extraordinary, showing a progression of complexity that the crew must have been tracking in their final hours, and among them is a vial labelled simply Threshold that contains structures so organized, so responsive to their chemical environment, that the mission's biologist refuses to classify them as non-living, inventing instead a new category she calls proto-animate, to describe chemistry that has crossed some invisible line into intentionality, into persistence, into something that wants to continue existing, even if it doesn't yet know how to reproduce. The research station goes up quickly, prefabricated modules anchored into stable ice with deep pylons, and within weeks they're operational, running experiments around the clock. And the first discovery is that the tiger stripes aren't static features, but dynamic, shifting slightly in response to tidal stress, opening new vents and closing old ones in a rhythm that repeats every Saturn orbit. And someone realizes that this rhythm itself might be crucial, that the periodic exposure to vacuum and radiation when vents seal might actually be part of the selection process, weeding out fragile chemistry and preserving only the structures robust enough to survive dormancy. They start mapping the entire E-ring in detail, tracking individual ice grains as they spiral outward from Enceladus, and they discover what the original crew suspected. The ring isn't uniform, it's structured, with distinct bands carrying different organic signatures depending on which vent they originated from. And the shepherd moons don't just randomly accumulate this material, they preferentially capture certain bands based on their orbital resonances, which means each small moon is receiving a curated selection of chemistry, not a random sample, and over geological time this non-random distribution could lead to different evolutionary experiments on different worlds, each starting with a slightly different toolkit. The implications spiral outward faster than anyone can track them. If this is happening at Saturn, then Jupiter's system must be even more complex, with Io's volcanic output adding sulfur chemistry to Europa's water, and Ganymede's magnetic field creating unique radiation environments that might drive entirely different reaction pathways. And someone points out that this means the Galilean moons aren't just 4 interesting worlds, they're 4 connected laboratories, running parallel experiments with slightly different initial conditions, and the results from one can propagate to the others through particle exchange and magnetic coupling. The Europa team, still operating in Jupiter's system, confirms this within weeks. They're detecting organic compounds in their ice cores that match Io's sulfur signature, mixed with native water chemistry in combinations that don't occur naturally on either world alone, which means the moons are collaborating, exchanging notes in a language written in chemistry and electricity. And the timescale for this exchange isn't human, it's geological. Millions of years of patient trading that has built up a chemical complexity neither world could achieve alone. Someone on the research station starts calling it the slow internet, and the name sticks. A network of worlds communicating through physical exchange of materials, through magnetic field interactions, through the gradual redistribution of particles by ring systems and plasmatoruses, operating on bandwidths measured in grams per century, but with a data capacity that spans billions of years. And the question becomes whether this network has been running since the solar system formed, or whether it took time to establish, whether there was a moment when the first organic molecules from one world reached another and found conditions suitable for survival, bootstrapping a process that has been accelerating ever since. The research team starts looking at older data with new eyes, re-examining images from the Voyager flybys in the 1980s, and they find evidence that the tiger stripes were active even then, probably active for millions of years before that, which means Enceladus has been seeding Saturn's system for geological ages, and if the process is that old, then some of the shepherd moons might contain not just proto-life but actual life. Organisms that have had millions of years to evolve in their tiny, frozen niches, and suddenly the mission profile changes again. They need to visit those moons with sterile equipment, need to be careful not to contaminate them with Earth life, or disrupt whatever processes might be unfolding there, and the ethics committees back home start arguing about whether humanity even has the right to study these worlds if they're already occupied, whether observation itself is a form of interference that could derail experiments that have been running since before humans existed. But the argument is academic because the missions are already launching, a fleet of small probes designed to visit every significant moon in Saturn's system with minimal contact, just spectroscopy and magnetic field mapping and particle collection. And what they find is staggering. Organic chemistry on every single world that spends time in the E-ring, increasing complexity correlated with proximity to Enceladus and with the duration of exposure, and on 3 of the smallest shepherd moons, the ones that orbit directly through the densest part of the ring, they find chemistry that's definitely animate. Microbial colonies living in ice-bound pockets, metabolizing sulfur compounds and perchlorate salts, and producing waste products that other colonies consume, creating little ecosystems barely visible under the highest magnification, but unmistakably alive, unmistakably structured, unmistakably doing what life does, persisting, adapting, spreading to every available niche. The discovery breaks across Earth like a wave, not the distant possibility of life on Mars, or the theoretical oceans of Europa, but actual, confirmed living organisms in Saturn's system, and the philosophical implications are immediate. Life isn't rare. It's not a fragile accident that requires perfect conditions. It's a natural consequence of chemistry plus energy plus time, and if it emerged in Saturn's system despite the cold and darkness and radiation, then it probably emerged in Jupiter's system too, and probably in the Uranian system, and probably around Neptune, and probably in the subice oceans of large Kuiper belt objects, and probably around other stars, and the Fermi paradox suddenly seems less paradoxical, because maybe the galaxy isn't silent. Maybe it's just that life spends its first billion years in places like this, quiet and cold and patient, and most of it never makes it to the stage where it builds radio telescopes. But that doesn't mean it's not there, not thriving in its own slow way, not mattering in the cosmic scheme. The research station on Enceladus becomes the most important scientific facility in human history overnight, and the crew expands to 30, then 50, then 100 as modules and supplies arrive on every available trajectory, and they start building outposts on other moons, on Titan where the methane seas might host entirely different chemistry, on Iapetus where the dark material coating one hemisphere might be organic fallout from ancient impacts on Hyperion whose spongy interior might harbour protected pockets of ancient ice with their own fossil record, and each outpost becomes a node in a growing human network that mirrors the slow internet they're studying. Information flowing between stations, observations building on each other, patterns emerging from the collective data that no single team could see alone. The geologist's theory, recovered from the data cores, becomes the framework everyone uses. Enceladus is the heart, the shepherd moons are the circulatory system, the E-ring is the bloodstream, and every world in Saturn's system is an organ with its own function, its own contribution to the larger metabolism, and just as no single organ in a body can be understood in isolation. No single moon in Saturn's system can be understood without reference to all the others, to the flows of material and energy that connect them, to the history they share and the future they're building together. Someone calculates that if the process continues at its current rate, if the complexity they're observing keeps increasing, then in another 10 million years, some of these moons might host not just microbial colonies, but actual ecosystems with specialized organisms, maybe even something like multicellular life. And in 100 million years, who knows, maybe intelligence, maybe civilizations that will look up at their ringed sky and wonder what's out there, never guessing that their world and its neighbours are all part of a single, interconnected system that has been growing and evolving since before their planet's current orbit was established. The research team start finding evidence of cycles, periods of high activity when Enceladus's plumes are stronger, followed by quiet periods when they nearly cease, driven by orbital eccentricities that vary over thousands of years, and they realise that these cycles themselves might be part of the selection process. That life in this system has to be adapted to feast and famine, to boom and bust, to waiting through dark periods and exploding during bright ones. And maybe that's another reason why it's so robust, because anything that survives here has already been tested by the harshest conditions imaginable. The Titan station starts reporting strange readings from the methane lakes, organic compounds at the bottom of Kraken Mare that look biological, but use a completely different solvent system than water-based life. And suddenly, there are two separate biospheres in Saturn's system, one based on water and ice, and one based on liquid hydrocarbons. And the question is whether they're related, whether organic material from Enceladus can rain down through Titan's atmosphere and seed the lakes below, whether there's exchange happening not just between water moons but across fundamental chemical divides, and if so, what kind of hybrid chemistry might emerge where the two systems overlap. The Jupiter team sends an update. They've found life on Europa, confirmed and undeniable, living in the ocean under the ice, and it's related to the life in Saturn's system, sharing enough genetic markers or chemical signatures that they must have a common origin, which means life doesn't just spread between moons within a single system. It spreads between systems, probably through asteroid impacts that launch material into solar orbit, and over billions of years those fragments can travel immense distances, can carry frozen organisms or at least frozen organic templates from Jupiter to Saturn to Uranus to Neptune and back again, making the entire outer solar system a single interconnected biosphere, a galactic-scale ecosystem held together not by proximity but by the patient exchange of materials across millions of years and billions of kilometres. The philosophical weight of this realisation settles over everyone slowly. Humans aren't discovering life, they're discovering life with a capital L, not as a phenomenon that happens in isolated pockets, but as a fundamental characteristic of the solar system itself, something that emerges wherever conditions allow and spreads through every available pathway, limited only by time and distance and the basic requirements of chemistry. And if this is true for our solar system, then it's probably true for every solar system, which means the universe isn't mostly empty space with rare islands of life. It's mostly life with rare islands of emptiness, and everywhere there's matter and energy and time. The slow, grinding process of chemical evolution is working toward complexity, toward organisation, toward something that eventually becomes aware of itself and starts asking questions about where it came from. The original pilot's observation, recovered from the final log entries, becomes the mission statement for everything that follows. We're not observers anymore, we're participants. We're part of the network now. Our ships and stations are nodes in the slow internet, and everything we do, every sample we take, every measurement we make, every piece of equipment we leave behind becomes part of the system's history, part of the data that future organisms or civilizations will have to interpret when they try to understand their own origins. And maybe that's okay, maybe that's inevitable, maybe the universe is full of civilizations that arose from chemistry that was accidentally cross-contaminated by previous civilizations, an infinite chain of influences stretching back to whatever the first life was, wherever it started, and maybe trying to be perfectly sterile is missing the point, because contamination is just another word for exchange, and exchange is how complexity grows. how systems become more than the sum of their parts. The research station on Enceladus celebrates its first full Saturn year of operation. 30 Earth years compressed into months of work that feels like decades, and they throw a party, awkward in low gravity, toasting with recycled water, while outside the plumes rise like clockwork, and someone says quietly that the original crew would have loved this, would have understood exactly what it means to watch the slow garden growing. And everyone is silent for a moment, thinking about the two explorers who gave everything to document the first evidence of the network, who became part of the ice they were studying, whose final samples are still yielding new discoveries 3 years later, and the station commander proposes a memorial. They'll place a marker at the coordinates where the suits were found, something permanent that will last for geological ages, and the inscription will be the geologist's final words from the data cache. Keep looking at the small moons, because that's where the real story is. And underneath, the pilot's final observation: we found the garden, and it's bigger than we thought. The marker goes up during the next EVA, a pyramid of machined titanium embedded deep in the ice, and around it they scatter some of the last samples the original crew collected, returning them to the environment they came from, completing a circle. And as they work, someone notices that the ice around the marker is already starting to develop the same patterns they've been observing elsewhere. The same organising principles, as if the organic material in the samples is teaching the native chemistry new tricks. And maybe that's fitting. Maybe that's exactly how the network grows, through exchange and mixing and the patient accumulation of innovations that get passed from world to world, generation to generation, species to species, civilization to civilization, until the distinction between native and foreign stops mattering because everything is connected, everything is related, everything is part of the same ancient experiment that began when the first organic molecules formed in the first protoplanetary disk and has been running ever since, spreading through every available pathway, turning the universe slowly, patiently, inexorably into a garden. The 5th year of operations brings the first evidence that the network extends beyond what anyone imagined. When a research team analysing meteorite impacts on the outer Shepherd moons discovers organic signatures that don't match anything in Saturn's system, compounds with isotope ratios pointing to origins in the Kuiper belt, frozen travellers that spent millions of years crossing the outer solar system before finally arriving here, and the implications cascade outward, like rings from a stone dropped in still water. If material from the Kuiper belt can reach Saturn's moons, then material from Saturn's moons can reach the Kuiper belt, and material from Jupiter can reach both, and suddenly the slow internet isn't just connecting the moons of individual planets, but linking every icy world in the solar system into a single vast web of chemical exchange that's been operating since the solar system's formation. The team starts modelling the trajectories, calculating how long it takes for material ejected from Enceladus's plumes to escape Saturn's gravity well, how it spreads through interplanetary space, how some fraction of it eventually collides with other worlds, and the numbers are staggering. Over the 4 billion years since the solar system stabilised, trillions of ice grains have made the journey from each active world to every other world, carrying their cargo of organic chemistry, their frozen libraries of molecular information, and even though the vast majority are lost to space or fall into the sun, or impact airless bodies where nothing can use them, the tiny fraction that lands in favourable environments is enough, given geological timescales, to seed the entire solar system with the products of every successful chemical innovation that's ever occurred anywhere. They find confirming evidence in the Kuiper belt data from the New Horizons extended mission, spectroscopic signatures on distant dwarf planets that match compounds first identified in Europa's ocean, and the researchers realise with mounting astonishment that they're looking at a postal system that's been running for billions of years, letters written in chemistry mailed from world to world at speeds measured in kilometres per second, taking millions of years to arrive, but arriving nonetheless, and every recipient world that has the right conditions can read those letters, can incorporate the information they contain, can build on it and send new letters of its own. The philosophical implications keep expanding. If the solar system is one connected network, then other solar systems must be networks too, and over the immense stretches of galactic time, material ejected from one star system can eventually reach others. Panspermia, not as a rare accident, but as an inevitable consequence of stellar dynamics, and the sheer patience of frozen chemistry. And maybe that's why life uses the same basic molecules everywhere researchers look. The same amino acids and nucleotide bases and lipid structures, not because these are the only possible solutions, but because they're the solutions that worked in some ancient system billions of years ago and have been spreading ever since, copied and modified and adapted but still recognisably descended from whatever the first successful chemistry was, wherever and whenever it emerged. The research program expands again, this time looking at the very oldest ices they can find, samples from the most ancient surfaces where material has been accumulating since the solar system formed, and in a preserved layer on one of Saturn's most distant irregular moons, captured long ago from a different orbit, they find organic compounds that predate the solar system itself, interstellar molecules that survived the nebula's collapse and the violent early period when planets were still forming. And these molecules carry their own story, hints of chemistry that occurred in the stellar nursery before there were planets at all, and someone realizes they're looking at evidence of pre-solar networks, chemistry that was already sophisticated when the sun was born, that came from previous generations of stars and planetary systems, an inheritance that goes back not just billions of years but potentially to the earliest epochs of the galaxy. A xenobiologist on the station starts calling it the galactic genome, the accumulated chemical knowledge of every successful origin of life that's ever occurred in the Milky Way, preserved in frozen grains that drift between stars. And while the information density is low and the transmission time is measured in millions of years and the error rate is astronomical, the system has been running for 10 billion years, and that's enough time for even the slowest network to build up a substantial library, to spread successful innovations across vast distances, to create a kind of chemical culture that transcends individual worlds and systems, and even individual epochs of star formation. The team starts looking for patterns in the distribution of organic compounds across different solar system bodies, trying to identify which innovations arose locally and which were imported, and they discover something unexpected. Certain complex molecules appear everywhere, on every world with the right conditions, but they always appear in the same sequence, as if there's a natural progression, a chemical ladder that systems climb one rung at a time, and this suggests that the evolution from simple organics to proto-life isn't random but follows predictable pathways constrained by thermodynamics and reaction kinetics, which means that anywhere in the universe with the right raw materials and energy sources is probably climbing the same ladder, possibly at different speeds, but following the same basic route. They test this hypothesis by examining the timeline of chemical evolution on different Saturn moons, comparing the progression on shepherd moons that have been in the E-ring for different durations, and the pattern holds. Younger exposures show simpler chemistry, older exposures show more complex chemistry, and the sequence is consistent, suggesting that given enough time and material input, all of these systems will eventually reach the same endpoint, whatever that endpoint is, whether it's simple self-replicating chemistry or something more complex, something that might deserve to be called alive. The implications for the search for extraterrestrial intelligence shift dramatically. If simple life is essentially inevitable given the right conditions, and if those conditions are common, and if life follows predictable pathways, then the question isn't whether aliens exist, but what stage different worlds and systems have reached in their chemical evolution, and whether there are predictable barriers or filters that prevent most systems from progressing beyond certain points, and what it means that Earth somehow passed those filters while presumably countless other worlds didn't. A theoretical biologist proposes what she calls the patient universe hypothesis, that the galaxy is full of worlds at every stage of chemical evolution, from the simplest organic compounds to proto-life, to simple organisms to complex ecosystems to intelligence. And the distribution follows a predictable curve with vast numbers at the simple end and progressively fewer at each stage of increasing complexity, not because the later stages are impossible, but because they take time, enormous amounts of time, and most worlds simply haven't had enough time yet, and Earth's intelligence is either a statistical fluke, arriving unusually early, or there's something about Earth-specific conditions that accelerated the process beyond the typical rate. The research station starts receiving data from the first dedicated Uranus mission in decades, and the findings confirm the pattern. Uranus's moons show the same kind of chemistry, the same progression of complexity correlated with exposure to material from active sources, and while Uranus doesn't have an Enceladus equivalent that's currently active, there's evidence that Miranda was geologically active in the past, possibly seeding the system during that period, and even now material arrives from interplanetary space, from other systems, keeping the slow chemistry working even in the absence of a local source. The Neptune data follows within months. Triton, captured from the Kuiper belt and still geologically active with its nitrogen geysers, is running its own version of the experiment, and the chemistry there is sufficiently different, influenced by nitrogen rather than water as the primary volatile, that it represents a parallel pathway, a different solution to the same basic problem of how to build complexity in a cold environment, and the researchers realise they're not looking at one way to make life but many. A whole space of possibilities that different worlds explore depending on their specific conditions, and maybe that's the real answer to why the universe seems so empty of radio signals, because most life doesn't follow the same pathway Earth did, doesn't emerge in warm oceans under thick atmospheres on rocky planets in habitable zones, but emerges instead in cold oceans under ice shelves in systems where sunlight is irrelevant and the energy comes from tides and radioactivity, and those systems don't build radio telescopes because they don't have access to fire or metallurgy or any of the technologies that require atmospheric chemistry, but they might still be alive, still conscious, still wondering if they're alone. Someone points out that humanity's presence in Saturn's system is itself becoming part of the network now, that the research stations are shedding organic compounds and metabolic byproducts, that the ships landing and taking off are distributing Earth chemistry across the moons they visit, and while the teams are trying to minimize contamination, complete sterility is impossible, which means in 1,000,000 years some future system, whether it's evolved from native Saturn chemistry, or from Earth contamination, or from some hybrid of the two, will find traces of human presence in the ice record and will have to interpret them. We'll have to decide whether these strange compounds indicate natural processes or artificial ones. And maybe they'll never know that they're the descendants, direct or indirect, of a process that humans accidentally accelerated by their simple presence. The ethical debates intensify. Should humanity try harder to prevent contamination? Should they abandon the research stations to preserve the natural evolution of Saturn's chemistry? Or is contamination inevitable and possibly even beneficial, a way of accelerating the slow internet, of providing new information to systems that might be able to use it? And maybe the whole concept of contamination is anthropocentric anyway, based on an outdated idea that each world's chemistry should be pristine and separate, when the reality is that worlds have been exchanging chemistry for billions of years, and Earth's contribution is just one more voice in an ancient conversation. The station commander makes a decision that surprises everyone. They're going to stop trying for perfect sterility. They're going to accept that humans are now part of Saturn's system, part of its metabolism, and instead of fighting that reality, they're going to study it, monitor how Earth chemistry interacts with native chemistry, see whether the hybrid systems that result are more or less complex than either parent system alone, treat the human presence as an experiment in accelerated exchange, in what happens when systems that evolve separately suddenly have access to each other's innovations, and maybe the results will tell them something important about how the slow internet works, about whether exchange always increases complexity, or whether there are conditions under which it causes interference instead. The next story is about to begin. Please relax and enjoy. The rain begins softly, a whisper against the window, and you stand beneath clouds so thick the afternoon feels like dusk. You know that above this grey ceiling, beyond the atmosphere's veil, there are not just stars, but suns. Countless furnaces of light, each burning with its own colour and tempo, each setting the rhythm for worlds you will never touch. Some blaze blue and fierce, living fast and bright. Others glow dim red, patient enough to outlast empires, galaxies, perhaps even time itself. And somewhere among them, on a world you cannot name, beneath a sky lit by a sun nothing like your own, someone might be standing as you are now, watching rain fall, wondering what lies beyond their clouds. In the cold depths between those distant suns, where starlight fades to nothing and the void stretches dark and infinite, there are clouds of a different kind. Molecular clouds, they're called. Great drifting masses of gas and dust, cold enough to freeze thought itself. Within these clouds, gravity works slowly, patiently, gathering material into knots the way a river gathers silt. Over millennia, these knots contract. The material falls inward, pulled by its own weight, and as it falls, it heats. Not quickly, not with flame or violence, but with the slow warmth of compression. the way your hands warm when you press them together. At the heart of each knot, something begins to glow, a protostar, barely visible through its cocoon of dust, surrounded by a disk of spinning material that will one day become planets, moons, asteroids, perhaps even life. You cannot see this process, of course. It takes millions of years, but imagine it anyway. The dust grains in that disk colliding and sticking, building pebbles from sand, boulders from pebbles, worlds from boulders. Jets of gas flicker along magnetic field lines, carrying away excess energy. The disk flattens as it spins, a cosmic phonograph record with the protostar as its needle. And all the while, the core grows denser, hotter, its atoms pressing closer together, their dance becoming frantic. Pressure mounts, temperature climbs, and then, at some threshold that cannot be predicted to the second but is nonetheless inevitable, hydrogen nuclei begin to fuse. The star ignites, light steadies. Outward pressure from fusion balances the inward crush of gravity, and the star joins what astronomers call the main sequence, the long, stable middle age during which most stars spend most of their lives. Where a star sits on that sequence depends entirely on its mass. Mass is destiny in the stellar world. A star with 10 times the sun's mass burns blue-white and fierce, exhausting its fuel in mere millions of years. A star with 1/10, the sun's mass, glows dim red, and sips its hydrogen so slowly it could burn for trillions of years, longer than the current age of the universe, longer than any measurement of time that holds meaning for human minds. Between these extremes lie all the gradations, white stars and stars, yellow stars, orange stars and amber stars, each with its own rhythm, its own lifespan, its own way of shaping the space around it. When you look at a star, you are looking at a message written in light. That light, when passed through a prism or a spectrograph, splits into a spectrum, a rainbow marked by dark lines where specific wavelengths have been absorbed. These lines are fingerprints. Each element in the star's atmosphere absorbs light at particular wavelengths. Hydrogen leaves its marks, calcium its own, iron and sodium and helium each signing their presence in the starlight. By reading these lines, astronomers determine what a star is made of, how hot it burns, even how fast it moves. If a star is approaching, its spectral lines shift slightly toward the blue, if receding, toward the red. Tiny shifts, but enough to reveal motion across the galaxy, enough to detect the gravitational tug of unseen planets pulling their stars into subtle wobbles. Most of the suns in the galaxy are red dwarfs, small, cool, patient M-type stars that make up perhaps 70% of all stars, but contribute almost nothing to the visible light of the night sky. They are too dim to see without telescopes, most of them, but they are everywhere, scattered through space like seeds. A red dwarf might burn for 10 trillion years, releasing its energy so slowly that the universe will have changed beyond recognition before it finally exhausts its fuel. Their habitable zones, the orbital distances where liquid water could exist on a planet's surface, are close in, so close that planets there are likely to be tidally locked, showing the same face to their star forever, one hemisphere in eternal day, the other in eternal night. And red dwarfs are restless. Their magnetic fields churn and twist, producing frequent flares that flood their inner systems with radiation. Any world in the habitable zone of a red dwarf must endure this flickering violence, this temperamental light that might strip atmospheres away, or perhaps drive evolutionary pressures toward resilience. A step up in mass and you find K dwarfs, orange stars that glow soft and steady, cooler than the sun but not as cool as red dwarfs, longer lived but not as patient. K-type stars offer a middle path. They burn for tens of billions of years, long enough for countless chances at complexity, yet they are calmer than their smaller siblings, less prone to violent flares. Their light is warm, autumn-tinted, and their habitable zones are wide enough, stable enough, that planets there might enjoy billions of years of gentle, predictable daylight. Time enough for oceans to form and life to experiment, to fail, to try again. Then there are stars like the Sun, G-type yellow dwarfs that sit in a comfortable middle range. The Sun has been burning steadily for 4.5 billion years and has another 5 billion to go before it exhausts the hydrogen in its core. That is enough time for continents to drift, for species to rise and fall, for intelligence to emerge and wonder at the stars. G-type stars provide steady, bright light without the intense ultraviolet radiation of hotter stars, or the temperamental flickering of cooler ones. They are Goldilocks stars, not too hot, not too cold, and their habitable zones are wide enough that planets can orbit at comfortable distances, spinning freely, enjoying day and night in regular cycles. But go higher in mass, and you find the fast burners, the A, B, and O stars that blaze white and blue. These are the stars that dominate star-forming regions, that sculpt nebulae with their fierce winds and ultraviolet light. They pour out energy at staggering rates, living only millions of years, sometimes only a few million, before exhausting their fuel. Around such stars, planets would be drenched in UV radiation, their atmospheres stressed, their surfaces harsh. There is little time for the slow work of evolution in such systems. By the time a world might settle into stable rhythms, its sun is already dying. All stars die, of course, but they die in different ways. When a star like the Sun exhausts the hydrogen in its core, fusion slows and gravity begins to win again. The core contracts, heats, and hydrogen in a shell around the core begins to fuse instead. This shell burning drives the outer layers outward. The star swells into a red giant, its surface cooling and reddening even as its core grows hotter. Red giants are gentle in a way, luminous but diffuse, their outer layers so tenuously held that stellar winds carry gas into space, enriching the interstellar medium with elements forged in the star's interior. Carbon, nitrogen, oxygen, ingredients for future stars and planets, drift outward in slow exhalation. Some giants pulse, their outer layers expand and contract in regular cycles, driven by instabilities in the way light moves through those enormous cool atmospheres. Cepheid variables pulse with periods measured in days or weeks, their brightnesses varying so predictably that astronomers use them as cosmic yardsticks, measuring distances across the galaxy. Our Lyrae stars pulse faster, with periods of hours. Mira-type giants pulse slowly, over months or years, their variability visible even to ancient watchers who saw them flare and fade in the night sky, mysterious breathing lights. Most stars are not alone. Perhaps half of all Sun-like stars, maybe more, are in binary systems, two stars orbiting a common centre of mass. Some binaries are wide, the stars separated by hundreds of astronomical units, each evolving independently. Others are close, their mutual gravity reshaping them. In some systems, one star pulls gas from its companion, drawing material through an invisible bridge between them. This mass transfer changes both stars, altering their evolution, sometimes producing spectacular outbursts as stolen gas spirals inward and heats. In the closest binaries, both stars may be locked in tight embrace, whirling around each other in hours or days, their surfaces nearly touching, their atmospheres mingling. Stars are also born in families, open clusters, loose gatherings of a few hundred to a few thousand stars, form together in molecular clouds, and then drift apart over tens or hundreds of millions of years. Globular clusters are older, denser, ancient spheres containing hundreds of thousands, or even millions of stars, relics from the early galaxy, orbiting the Milky Way's halo like loyal attendants. Because all the stars in a cluster formed at roughly the same time from the same material, clusters are laboratories for understanding stellar evolution. The most massive stars have already died, the smallest are still burning. By studying which stars remain and which are gone, astronomers piece together timelines of stellar life. Within each star's light is a record of its birth. Astronomers call elements heavier than helium metals, regardless of what they actually are. Carbon, oxygen, iron, all lumped together under that term. A star's metallicity tells you when it formed. The first stars, born in the pristine hydrogen and helium left over from the Big Bang, had almost no metals at all. When those stars died, they scattered heavier elements into space. The next generation of stars formed from slightly enriched gas. With each generation, the metallicity increased. Today's stars, formed from clouds enriched by billions of years of stellar death, carry the signatures of countless previous lives in their spectra. Low metallicity stars are ancient voyagers, time capsules from the early universe. High metallicity stars are recent arrivals built from the ashes of many predecessors. Stars also have weather. Rotation and convection in a star's outer layers generate magnetic fields, and those fields erupt through the surface in complex patterns. Sunspots are magnetic knots where the field suppresses convection, cooling the surface and creating dark patches. Flares are sudden releases of magnetic energy, flooding space with radiation and particles. Coronal mass ejections hurl billions of tons of plasma outward at high speed. All of this affects any planets orbiting the star. Planetary magnetic fields channel these particles toward the poles, producing auroras, curtains of light in the upper atmosphere. Over time, stellar winds can erode atmospheres, especially on planets without strong magnetic shields. The star's weather becomes the planet's destiny. We find those planets by watching the stars. When a planet crosses in front of its star from our perspective, the star's light dims slightly, a transit. By measuring the depth and duration of the dimming, astronomers determine the planet's size and orbital period. If the transit happens repeatedly, precisely on schedule, it confirms a planet is there. Sometimes, during a transit, starlight filters through the planet's atmosphere, and the spectrum of that light carries the chemical fingerprints of atmospheric gases, water vapour, methane, carbon dioxide. We are learning to read planetary atmospheres from trillions of miles away, to taste the air of worlds we will never visit. We also find planets by watching stars wobble. A planet's gravity tugs its star, pulling it into a small orbit around the system's centre of mass. As the star moves toward us and away, its spectral lines shift, Doppler shifts, the same effect that changes the pitch of a passing siren. By measuring these shifts over time, astronomers determine the planet's mass and orbit. Combined with transit data, this gives a complete picture: size, mass, density, orbit. Rocky worlds and gas giants, hot Jupiters hugging their stars and ice giants drifting far out, all revealed by the star's subtle dance. There are other methods, rarer but powerful. Direct imaging captures the light of giant planets orbiting far from their stars, young worlds still warm from formation. Gravitational microlensing detects planets by the way their gravity bends the light of a more distant background star, a fleeting alignment that might happen only once and never repeat. Astrometry tracks the star's position on the sky, measuring its motion over years or decades to reveal the pull of long-period companions. Each method has its strengths, its biases, its blind spots. Together, they map the diversity of planetary systems, and as we find these worlds, we ask, could they harbour life? The answer depends on their stars. A star's type sets the boundaries of its habitable zone, the range of distances where temperatures allow liquid water. Red dwarfs have narrow habitable zones close to the star, where planets might be tidally locked and battered by flares. K and G stars offer wider, calmer zones. Blue stars flood their surroundings with UV radiation and change too fast, dying before life has time to gain a foothold. But habitability is not just about water. It's about stability, about time, about the kind of light that falls on a world's surface and the rhythms that light imposes. Imagine standing on a planet orbiting a red dwarf. Noon might be copper-tinted, the sun a dim red disk hanging motionless in the sky if your world is tidally locked. One side of your planet bakes in eternal day, the other freezes in eternal night, and only in the twilight band between them, where winds howl from the heat toward the cold, might conditions be tolerable. Or imagine a world around a blue-white star, where daylight is icy pale and intense, where summers are fierce and brief, where the star's brightness fluctuates as it pulses through instabilities. The colour of daylight shapes vision, photosynthesis, the very chemistry of life. The length of day and year sets rhythms for behaviour, metabolism, sleep. All stars end. The smallest red dwarfs will burn until they have fused all their hydrogen, then cool slowly into hypothetical white dwarfs, a fate that awaits them trillions of years from now, so far in the future that it's uncertain whether the universe will still resemble anything we'd recognise. Sun-like stars swell into red giants, shed their outer layers as glowing shells called planetary nebulae, and leave behind white dwarf cores, Earth-sized embers, hot but no longer fusing, slowly cooling over billions of years. Massive stars die violently. When their cores run out of fuel, they collapse in milliseconds, triggering supernovae that outshine entire galaxies for weeks. These explosions forge the heaviest elements, iron, gold, uranium, and scatter them into space. The shock waves from supernovae compress nearby clouds, triggering new star formation. Death and birth intertwined, the galaxy recycling itself. Stars are also travellers. They form in nurseries, dense regions within molecular clouds, where dozens or hundreds of stars ignite within a few million years of each other. After birth, the stellar winds and radiation from the hottest stars disrupt the remaining gas, and the cluster begins to disperse. Some stars drift into loose-moving groups, sharing similar velocities as they orbit the galactic centre. Others scatter, becoming isolated field stars. The Milky Way is crisscrossed with stellar streams, trails of stars pulled from clusters or small galaxies by tidal forces, evidence of the galaxy's ongoing assembly. By mapping stellar motions, ages and compositions, astronomers reconstruct the Milky Way's history, tracing merger events, identifying in falling satellites, watching the slow churn of galactic evolution. The rain continues, steady now, and you think about how strange it is that you can know these things. That light, travelling for years or centuries or millennia, carries information encoded in wavelengths and intensities, and that human minds, evolved to navigate savannas and recognise faces, can decode that information, can reconstruct the lives of suns they will never see up close. Behind the clouds above you, the sun is setting, though you cannot see it. And beyond the sun, thousands of light years away, a red dwarf is flaring, its planets huddled close, their atmospheres straining. A K-type star rotates slowly, its habitable zone calm and wide, its world cycling through gentle seasons. A binary system exchanges gas in a glowing stream. A Cepheid variable swells and contracts, its light pulsing like a heartbeat visible across the galaxy. A blue supergiant burns through its final reserves, months or years away from its explosive end. You will never visit those places. No one alive today will. But you can know they exist. You can understand, in outline if not in detail, the forces that shape them, the physics that governs them, the timescales on which they change. You can look at the spectra of stars and read their compositions, their ages, their motions. You can watch a star dim and know a planet has passed in front of it. You can measure a star's wobble and calculate the mass of an unseen companion. These are not small achievements. They are evidence of something remarkable about intelligence, about curiosity, about the human refusal to accept the night sky as mere decoration. The galaxy is full of quiet hearts. Most stars burn unnoticed, too dim or too distant to catch the eye. They do not care whether anyone watches them. They fuse hydrogen into helium, helium into carbon, some of them carbon into heavier elements still, following the logic of nuclear physics with no awareness, no intention, no purpose beyond the balance of gravity and pressure. And yet they create the conditions for everything else. They forge the elements that make planets, atmospheres, oceans, life. They provide the energy that warms worlds, that drives weather, that powers photosynthesis and all the cascading complexity that follows. They set the clocks by which days and years are measured, the rhythms to which life adapts. You think about the first humans who looked up and wondered what the stars were. They made stories, connected dots into constellations, imagined the stars as distant fires or holes in the sky or the eyes of gods. They had no way to know the truth was stranger and more beautiful than any story, that each star was a sun, that some had planets, that those planets might have weather and seasons and perhaps even life, looking back across the light years with their own questions. For most of human history, the stars were unreachable, unknowable. Now we reach them with light. Spectroscopy and photometry, interferometry and astrometry, all the ways we've learned to extract meaning from photons that have travelled unimaginable distances. The rain is easing now, the clouds beginning to break. A patch of sky appears, still bright with late afternoon light. No stars visible yet, but they are there. They are always there. Tens of billions of them in this galaxy alone, each with its own story written in light, its own cycle of birth and death, its own contribution to the slow alchemy that turns hydrogen into everything else. Some are giants, luminous enough to be seen across the galaxy. Some are dwarves, invisible beyond a few light years. Some are young, still surrounded by the disks from which planets are forming. Some are old, white dwarfs cooling in the dark, or neutron stars spinning in silence, or black holes marking where the most massive stars once burned. And around some of those stars, around how many, we still don't know, there are worlds. Rocky worlds and gas giants, ice giants, and lava worlds, planets with thick atmospheres and planets with none, worlds where volcanoes erupt under red light, where oceans freeze and thaw with the star's brightness, where storms rage for centuries, where surfaces are scoured by radiation or sheltered by magnetic fields. Worlds where maybe life has emerged, simple at first, perhaps staying simple, perhaps evolving into complexity, perhaps achieving intelligence, perhaps looking out at their own night sky and wondering, as you're wondering now, what lies beyond. You cannot know if anyone is out there looking back. The distances are too vast, the timescales too long, the chances too uncertain. But the question itself is worth holding. It changes how you see the rain, the clouds, the patch of clearing sky. It reminds you that you are standing on a planet orbiting a G-type star, that this star is one of hundreds of billions, that each of those stars has its own character, its own rhythm, its own influence on the space around it. It reminds you that the universe is not a static backdrop but a living system, constantly changing, constantly creating new conditions, new possibilities. The rain stops, the clouds drift east, the first stars appear, faint against the still bright sky, growing more visible as twilight deepens. You do not know which ones have planets, which ones are red dwarfs or blue giants or yellow dwarfs like the sun. But you know they are all suns, all burning, all shaping the worlds that orbit them. Their quiet hearts beat in fusion rhythms, setting the time for everything that happens near them, and their light, filtered through space and time, tells you their stories, stories written in spectra and brightness variations, in wobbles and transits, in the elements they forge and the winds they blow and the ways they change the darkness around them. You stand there a little longer, watching the stars appear, thinking about all those distant suns and the worlds that circle them, the rhythms they set, the possibilities they hold. The air has grown cold, the kind of cold that settles after rain, when moisture still clings to everything and the earth releases its stored warmth into the clearing sky. You can smell the wet pavement, the soil, the faint green scent of plants breathing in the dark. These are the smells of a world shaped by a particular star at a particular distance, with a particular atmospheric composition and magnetic field and axial tilt. Everything about this moment, the temperature, the oxygen you breathe, the water that just fell from the sky, exists because of where Earth sits in the sun's habitable zone, because of how the sun burns, because of what the sun is. But you are thinking beyond this world now. You are thinking about those planets around red dwarfs, where the habitable zone is so narrow that a planet must orbit its star in a matter of days or weeks, so close that tidal forces lock one face eternally toward the dim sun. On such a world, there would be no sunrise, no sunset, no daily cycle to mark time. The star would hang fixed in the sky, a dull ember casting long shadows, and everything would arrange itself according to that geometry. Weather patterns flowing from the hot side to the cold, ecosystems clustering in the twilight regions where temperatures are tolerable, evolution proceeding under constraints utterly unlike those on Earth. If intelligent life arose there, what would they make of their sky? Would they even think to look up? Or would their attention always be drawn horizontally toward the terminator where day meets night, toward the liminal spaces where their world is most habitable? And what of the planets around K-dwarfs, those patient orange suns? There, days and nights would cycle normally, but everything would happen more slowly, more gently. The star would live longer than the sun, offering more time for complexity to develop, for ecosystems to mature, for intelligence to emerge and build and wonder. The light would be warmer, more amber than Earth's sunlight, and photosynthesis might work differently there. Plants and algae tuned to a spectrum shifted toward the red. Autumnal light, year-round, never harsh, never scorching. A world like that might be gentler than Earth, its weather less violent, its seasons more measured. Or perhaps not. Perhaps the slower stellar winds would allow thicker atmospheres to accumulate, turning such worlds into pressure cooker greenhouses. Or perhaps the stability would breed stagnation, ecosystems settling into equilibria that resist change. You try to imagine what it would be like to live under a blue sun, an A-type or B-type star burning bright and hot. The light would be strange, pale and intense, flooding the world with ultraviolet radiation, that would require any life to develop sophisticated protective mechanisms. Thick ozone layers, UV-absorbing pigments, perhaps living underground or underwater during the star's brightest hours. The star itself would be young, a few million or tens of millions of years old at most, and in another few million years it would begin its death throes, swelling and brightening and finally exploding. There would be no deep time on such a world, no billions of years for evolution to tinker and refine. Any life there would have to arise quickly, adapt quickly, live quickly, always under the ticking clock of the star's inevitable end. Perhaps that urgency would drive rapid evolution, or perhaps it would make complexity impossible, life never able to gain more than a fragile foothold before being erased. These thoughts lead you to consider the planets that orbit binary stars, those systems where two suns share the sky. Some of these systems are widely separated, with planets orbiting just one star while the companion shines as a brilliant point of light in the sky. A second sun that never rises or sets, just slides along its slow path through the constellations. But in closer binaries, planets might orbit both stars in figure-8 or circumbinary orbits, and there the sky would be truly alien. Two suns rising at different times, casting double shadows, their combined light shifting in colour and intensity as their orbits bring them closer and farther apart. Eclipses would be common, one sun passing in front of the other, the world plunged into partial darkness in the middle of the day. Seasons would be chaotic, unpredictable, governed not by axial tilt alone but by the complex gravitational dance of two stars pulling the planet along elliptical paths. What kind of life could evolve under such conditions? What kind of calendars would such a civilization develop? What kind of myths would they tell about their twin suns? The sky is darker now, the stars more numerous. You recognise a few constellations, Orion rising in the east, the Pleiades higher up, their clustered stars so young they still glow blue, having formed only 100 million years ago, cosmic infants. The Pleiades are sisters in more than mythology. They truly were born together, condensing from the same molecular cloud, and they still travel together through space, their motions linked. In a few 100 million years they will drift apart, scattered by gravitational interactions with other stars and giant molecular clouds, each sister going her own way, their family dissolved into the wider population of the galaxy. But for now they remain together, a visible reminder that stars have histories, relationships, origins. You think about the globular clusters you cannot see, those ancient spheres of stars orbiting the Milky Way's halo, each cluster containing hundreds of thousands of stars packed into a sphere only tens of light years across. The stars there are old, 10 billion years or more, formed when the galaxy itself was young. In the core of a globular cluster, stars are separated by only light weeks or light months instead of light years, and their sky would be filled with bright stars, hundreds of them as bright as Venus appears from Earth, the night never truly dark. But those stars are metal poor, forged before the galaxy had been enriched with heavy elements, and it is unclear whether planets could even form around them, whether there is enough silicon and iron and carbon to build rocky worlds. Perhaps life in globular clusters is impossible, or perhaps it is merely different based on chemistry we have not imagined. The thought of alien chemistry leads you down another path. Life on Earth is based on carbon, water, and a few dozen other elements, all forged in stars and scattered by supernovae. But the availability of those elements varies across the galaxy. Stars formed in the outer regions of the Milky Way, far from the dense star-forming regions of the spiral arms, are metal poor. Stars formed near the galactic centre, where star formation has been intense and supernova frequent, are metal rich. Does this mean life is more common in some regions than others? Are there galactic habitable zones, not just stellar ones, regions where the density of heavy elements is high enough to form rocky planets, but not so high that the star formation rate produces too many supernovae, sterilizing nearby systems with gamma rays and cosmic rays? And what of the elements themselves? Every atom of carbon in your body was forged in the core of a red giant, where helium nuclei fuse together in the triple alpha process, a reaction so delicate that it requires a precise resonance. In the carbon nucleus, a quantum coincidence that seems almost designed to allow carbon's existence. Every atom of oxygen came from heavier stars, where neon and magnesium burning produced oxygen as a byproduct. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all of it created in the cores of massive stars, then ejected in supernova explosions, spreading through the interstellar medium, mixing with hydrogen and helium, eventually collapsing into new stars and new planets. You are quite literally made of stars your atoms cycled through multiple generations of stellar birth and death, before finally assembling into the form standing here under the clearing sky. This recycling is ongoing. Right now, somewhere in the galaxy, a star is exploding, and in the heat and pressure of that explosion, nuclei are being slammed together to create elements that do not exist elsewhere, elements heavier than iron like gold and platinum and uranium. Those elements will drift outward in an expanding shell of gas and dust, cooling as they go, eventually encountering a molecular cloud. The shock wave from the supernova will compress the cloud, triggering new star formation, and some of the heavy elements will be incorporated into the next generation of stars and planets. In this way, the galaxy gradually becomes more metal-rich over time, each generation of stars chemically distinct from the last, a slow enrichment that has been ongoing for more than 10 billion years. You wonder if there are planets where life developed earlier than on Earth, around stars formed when the galaxy was younger, its metallicity lower. Would such life be fundamentally different, working with a more limited palette of elements? Or would the same chemistry prevail? Carbon and water and oxygen forming the backbone of biology everywhere, regardless of when the planet formed. And what of life that might develop later, billions of years from now, on planets around stars not yet born, formed from clouds enriched by countless more generations of supernovae? Would those organisms have access to heavier elements in such abundance that their biochemistry could explore possibilities unavailable to Earth life? The temperature continues to drop. You can see your breath now, faint wisps of vapour catching the last light from the western horizon. Water vapour, H2O, 2 hydrogen atoms and 1 oxygen atom, the former from the Big Bang, the latter from a long-dead star. This simple molecule, so common in the universe that it forms vast clouds in space and ice mantles on interstellar dust grains, is the medium of life on Earth, and likely on many other worlds. But water is strange. It expands when it freezes, making ice float, a property that keeps Earth's oceans from freezing solid from the bottom up, allowing life to persist through ice ages. It has a high heat capacity, moderating temperature swings. It is an excellent solvent, allowing the chemistry of life to proceed in liquid form. These properties are consequences of water's molecular structure, the way oxygen hogs electrons and gives the molecule a lopsided charge distribution, allowing water molecules to hydrogen bond to each other. Would alien biochemistry necessarily use water? Or are there other solvents, ammonia, methane, even liquid methane on cold worlds like Titan, that could serve the same purpose? You shake your head, smiling at the way your thoughts spiral outward, each question leading to more questions, the universe revealing itself as infinitely more complex and strange than you can fully grasp. But that is the joy of it, is it not? That there is always more to learn, more to wonder about, that every answer opens new mysteries. The stars above you are not just points of light but puzzles, each one a laboratory, running experiments in nuclear physics, hydrodynamics, magnetohydrodynamics, each one producing conditions that do not and cannot exist on Earth. By studying them, by analysing their light and tracking their motions and modelling their interiors, astronomers are doing more than cataloguing the cosmos. They are learning the fundamental rules that govern matter and energy, the constraints within which everything, stars, planets, life intelligence must operate. And now, finally it is fully dark, the clouds entirely gone, the sky a deep blue-black scattered with stars. You pick out a few more constellations, Cassiopeia, Andromeda, Perseus, and you remember that the faint smudge near Andromeda, barely visible to the naked eye, is not a star at all but another galaxy, M31, the Andromeda Galaxy, a spiral like the Milky Way, containing hundreds of billions of its own stars, its own molecular clouds, its own planets, and perhaps its own instances of life and intelligence. That galaxy is 2.5 million light-years away, meaning the light you see left there 2.5 million years ago, when the first members of the genus Homo were beginning to walk upright on the African savanna. You are seeing Andromeda not as it is now, but as it was then, and if anyone in Andromeda is looking back at the Milky Way, They are seeing it as it was 2.5 million years ago, long before humans existed. This time delay, this light travel time, means that the universe you perceive is not the universe as it exists in some objective now. There is no universal now. Every star you see is a message from the past, some more distant than others, and the farther you look, the further back in time you see. The most distant objects visible to telescopes, galaxies near the edge of the observable universe, are seen as they were more than 13 billion years ago, when the universe itself was young, when the first stars were just beginning to form. Those galaxies may no longer exist. Their stars long since burned out or collapsed into black holes, but their light is only now reaching us. Ghosts from a universe that no longer exists in the form we perceive. You turn your gaze back to the nearer stars, the ones you can see without a telescope. Sirius, the brightest star in the night sky, is only 8 light-years away, close enough that its light is recent, showing you the star almost as it is now. Betelgeuse, in Orion's shoulder, is a red supergiant, bloated and unstable, somewhere between 400 and 600 light-years away. When you see it, you're seeing it as it was in the 1400s or 1500s, during the Renaissance, and it is possible, unlikely but possible, that Betelgeuse has already exploded, that the shockwave and light from that explosion are racing toward Earth right now, unseen, and will arrive tomorrow or next year or 100 years from now, suddenly making Betelgeuse as bright as the full moon for weeks or months before it fades. No one knows when Betelgeuse will explode, only that it will, that it is near the end of its life, that its core is a tangle of fusion shells burning different elements, the star struggling to maintain equilibrium as gravity tries to crush it, and fusion pressure tries to blow it apart. When Betelgeuse does explode, it will be spectacular. For a few weeks it will outshine every other star in the sky except the Sun. Ancient records will be searched for omens and myths, new ones will be created, and astronomers will point every telescope on Earth and in space at it, capturing data about a supernova closer than any in recorded history. The explosion will create a neutron star or perhaps a black hole, and it will seed the interstellar medium with new elements, enriching the clouds from which future stars will form. And then, over tens of thousands of years, the ejected material will expand and cool and fade, leaving behind only a faint nebula and the compact remnant, and the constellation of Orion will be subtly different, one of its brightest stars gone, replaced by a dimmer point, a stellar remnant barely visible except in infrared or X-ray wavelengths, the ghost of a giant that once was. You realize that you have been standing outside for longer than you intended, that the cold has worked its way into your fingers and toes, but you are reluctant to go inside just yet. There is something about this moment, this particular arrangement of sky and thought and silence, that feels important to hold on to. The stars have always been there, of course, every night of your life, every night of every human life that has ever been lived. But how often do you actually look at them, actually think about what they are? How often does anyone? Modern life pulls attention downward and inward, to screens, to immediate concerns, to the small sphere of influence that defines daily existence. The stars become backdrop, decoration, something noticed only in passing, if at all. But they deserve more than passing notice. Each one is a story, a process, a set of conditions playing out over timescales that dwarf human comprehension. That red point of light low on the horizon might be a dying star, swollen and cool, in its last million years before shedding its outer layers. That white point might be a young star, still surrounded by a disk of planet-forming material, worlds coalescing from dust even now. That steady yellow point might be hosting a planet where rain is falling, where oceans are stirring, where something lives and moves and perhaps even thinks. You cannot know, the distances are too great, the observations too difficult. But the possibilities are there, written into the physics of stars and planets, statistical inevitabilities emerging from the vast numbers involved. The Milky Way itself is visible now, a faint band of light arching overhead, dense in some regions and sparse in others. You are looking edge-on into the disk of the galaxy, seeing the combined light of billions of stars too distant to resolve individually. The dark patches are not empty space but dust clouds, regions where new stars are forming, blocking the light of stars beyond. The brightest regions are the spiral arms, where star formation is most active, where massive blue stars light up their surroundings before dying young. The galaxy is rotating, all these stars orbiting the common centre where a supermassive black hole weighing millions of solar masses sits quietly, its gravity holding everything together. The Sun orbits that centre once every 230 million years or so, a galactic year, and it has completed about 20 such orbits since it formed. 20 trips around the galaxy during which continents have assembled and broken apart. Species have risen and gone extinct. The whole drama of Earth's history replaying 20 times over while the Sun traces its vast circle. And the galaxy itself is moving, falling toward the Andromeda Galaxy under mutual gravitational attraction. In about 4 billion years, the two galaxies will collide, though collide is perhaps the wrong word, since stars are so widely separated that actual stellar collisions will be rare. Instead, the galaxies will pass through each other, their gravitational interactions flinging stars into new orbits, triggering bursts of star formation as gas clouds collide and compress, eventually merging into a single larger galaxy. The Sun will likely survive this encounter, though it might be flung into a different orbit, perhaps farther from the galactic centre, perhaps closer. Earth might survive as well, or it might not. By then the Sun will be well into its red giant phase, and Earth's fate depends more on the Sun's evolution than on the galactic merger. But the night sky, 4 billion years from now, will be dramatically different. Andromeda no longer a distant smudge, but a vast band of light dominating half the sky, its stars mingling with the Milky Ways, the whole system in glorious chaos. You find yourself wondering what humans, or whatever humans become, will make of that sky. Will there still be observers, still beings capable of looking up and understanding what they see? 4 billion years is a long time, longer than life has existed on Earth, long enough for evolution to produce outcomes utterly unlike anything alive today. Or perhaps intelligence will have moved beyond biological substrates entirely, uploaded into machines or distributed across networks spanning star systems, no longer bound to planets, or even to matter as we understand it. Or perhaps intelligence will have destroyed itself, a brief flicker in cosmic time, leaving Earth silent again, its atmosphere gradually stripped away by the aging Sun, its oceans boiled off, its surface eventually sterilized and dead. There is no way to know. The future is not written in the stars, only probabilities and possibilities, the outcomes of processes too complex to predict in detail. But standing here now, under these stars, you feel a strange sense of continuity with all the other humans who have looked up and wondered. Ancient astronomers tracking the movements of planets, trying to predict eclipses and conjunctions. Medieval scholars debating the nature of the celestial spheres, whether the stars were holes in a crystalline dome or distant suns. Renaissance observers peering through the first telescopes, discovering moons around Jupiter and phases of Venus, realizing that the Earth was not the centre of everything. Victorian spectroscopists analysing starlight, discovering that the same elements present on Earth existed in the stars, that the universe was made of comprehensible matter following comprehensible laws. 20th century astronomers discovering the expansion of the universe, the cosmic microwave background, the acceleration of that expansion driven by something called dark energy that no one yet understands. And now, 21st century observers finding planets around other stars, measuring their atmospheres, searching for biosignatures, beginning the long process of determining whether life is common or rare, whether intelligence is inevitable or unlikely. Each generation builds on the work of previous generations, the accumulation of knowledge a long collaborative project spanning centuries, millennia. No one person understands all of it. The universe is too large, too complex, the details too intricate for any single mind to hold. But collectively, the species knows more than it ever has, and that knowledge continues to grow, every new telescope revealing new puzzles, every new measurement refining our understanding or overturning old assumptions. It is a hopeful thought in a way. Despite everything, despite wars and famines and plagues, despite the petty cruelties and grand tragedies that fill human history, there has always been this thread of curiosity, this drive to understand, to look beyond the immediate and grasp at larger truths. The cold is becoming uncomfortable now, insistent. You stamp your feet, blow on your hands, knowing you should go inside but still reluctant to leave. Above, the stars continue their slow procession across the sky, rising in the east and setting in the west, the apparent motion caused by Earth's rotation, the planets spinning beneath the fixed stars. Except the stars are not fixed at all. They are all in motion, orbiting the galaxy, some moving faster and some slower, some heading toward the galactic centre and some away, the whole system in constant flux. The constellations you see are temporary arrangements, patterns that happen to exist now, but will change over thousands and millions of years as the stars drift relative to each other. The Big Dipper will not always look like a dipper. Orion will not always look like a hunter. The sky is not static but evolving, and if you could watch it in fast forward over millions of years, you would see the stars sliding past each other like boats on a river, the familiar patterns dissolving and new ones forming, the sky continually remaking itself. You think about the people who will stand here in the future, 1,000 years from now, 10,000, 100,000. Will they still look up? Will they still wonder? Or will the stars have become so familiar, so mapped and catalogued and understood that they lose their power to inspire awe? You hope not. You hope that no matter how much is learned, there will always be deeper questions, mysteries that retreat as you approach them, phenomena that surprise and confound. The universe seems constructed that way, every answer revealing new questions, every solved puzzle showing 10 more waiting behind it. Quantum mechanics and general relativity, the two most successful theories in physics, are incompatible with each other, both correct within their domains but unable to be unified into a single framework. Dark matter and dark energy together make up 95% of the universe's mass energy, and no one knows what they are. The fundamental constants of physics, the speed of light, the strength of gravity, the charge of the electron, have the values they have for no known reason, and if they were even slightly different, stars could not form, chemistry could not work, life could not exist. Are those constants truly constant, or do they vary across space and time? Are there other universes where they have different values? And if so, are those universes real in the same sense this one is? Or are they mathematical abstractions, hypotheticals that exist only in equations? These questions have no answers yet, may never have answers, but they are worth asking. They frame the boundaries of knowledge, the places where understanding fades into speculation and philosophy, and they remind you that for all humanity has learned, the universe remains fundamentally mysterious, its depths unexplored, its possibilities vast. Standing under these stars, you are standing at the edge of the known world, looking out into darkness that is not empty but full of stars too distant to see, galaxies beyond counting, structures and phenomena that do not yet have names. And somewhere in that vastness, perhaps, others are standing as you are, looking up at their own skies, wondering about the nature of things, asking the same questions in different languages, seeking the same understanding. The thought makes you feel both small and connected. Small because you are one organism on one planet, orbiting one unremarkable star in a galaxy, containing hundreds of billions of stars in a universe, containing hundreds of billions of galaxies, and connected because that very awareness, that ability to comprehend scale and distance and time, is itself remarkable, a product of 4 billion years of evolution, producing nervous systems complex enough to model the universe, to hold abstractions, to wonder about things far removed from immediate survival needs. Consciousness is rare, as far as anyone knows, possibly unique to Earth, possibly scattered across the galaxy, possibly common but never long-lasting, each instance flickering briefly before extinction. But however rare it is valuable, this capacity to know and question and care. It is what allows the universe to know itself, to examine its own structure and history, to ask why it exists and whether it means anything. You do not have answers to those questions, and you suspect no one does. But you have this moment, this experience of standing under stars on a cold night after rain, your mind full of thoughts about fusion and gravity and time, your body full of atoms forged in stars, your consciousness a brief eddy in the flow of matter and energy that constitutes the universe. It is enough. It has to be enough. The stars do not care whether you understand them, do not notice your attention, will continue burning long after you're gone. But you are here now, aware and alive, capable of appreciating them, and that seems like something worth protecting, worth preserving, worth passing on to whatever comes next. Finally, because you must, you turn away from the sky and walk toward the warmth and light of your home, but you carry the stars with you, their quiet light imprinted on your thoughts, their distant fires still burning in your mind. Tomorrow the rain might return, the clouds might cover everything again, and you will go about your day without thinking of stars at all. But they will still be there, above the weather, beyond the atmosphere, burning steadily in the dark, red dwarfs and blue giants, yellow stars and orange stars, binaries and variables, clusters and streams, all the quiet hearts of other suns, all the possibilities they hold, all the worlds they warm, all the stories they tell to anyone willing to listen.